Anil sir, we will start the session, sir.
Yes, ma'am.
So good evening to one and all. So I welcome you once again for the day 2, session 3 and 4 for the 6-day ATAL online FDP on VLSI design innovations for defense applications. So now today we have with us Mr. C.H. Manikanda, sir is from MOS Chips, Hyderabad. So to introduce the guests, now I call upon Dr. T. Gitama, Associate Professor, to introduce the guests to all the participants.
Okay, ma'am. Thank you. Good evening, Manikanta. Good evening to all participants. It's my pleasure to introduce today's resource person, Mr. Manikanta. Mr. Manikanta is a senior physical design engineer with 6 years of experience in the VLSI industry, currently working at MOS Chips Technologies. He has a strong background in physical design by contributing to the design, development, and optimization of semiconductor chips. His expertise spans various aspects of the VLSI physical design flow, including floor planning, placement, routing, and timing closure, which are crucial for ensuring the performance and reliability of integrated circuits. He completed post-graduation from GMR Institute of Technology in 2016, BTech degree from Chaitanya Engineering College in 2013. Mr. Mankanta is passionate about advancing career in physical design, staying updated with latest industry trends and tools. His goal is to contribute cutting-edge technologies in semiconductor design and to play a role in the development of innovative solutions in the industry. Thank you, Manikanta. Please continue the session.
Thank you, ma'am. First of all, thank you for giving me this opportunity. As I'm the former student of GMRIT, I'm very happy to take the class for you. Thank you. Can you share my screen, Andy?
Yes, sir. Yes, sir.
Yes, sir.
Yeah, sure. Yeah, is it visible, Andy?
Yes, sir.
Yes, sir.
Yeah. Actually, coming to the VLSI, everyone we are talking about the technology. Okay. So main thing, what is the logic technology? So everyone we know that we are coming from the BZT right now, CMOS, from CMOS to right now it is FinFET. Okay.
Sir,
So
excuse
we are
me, sir.
coming.
Sir, full
Yeah.
screen mode is not enabled, sir.
Okay, sure.
Sir.
Is it okay now?
Yes, sir. Yes, sir. Now it's perfect, sir.
Yeah, sure. Okay. Yeah. We are talking about the technology, right? So what is this technology? What is what in this technology in the VLSI? Okay. So in the initial days, we are using the BZTs. You know that BZT. After that, we are coming to the NMOS, PMOS. Over that, we came to the CMOS. After that, we are right now we are using the FinFET technology. So already we know that what is the advantage over the BZT or over the CMOS. What is the FinFET? Everything we know already that. So in this PPT, what I will explain that in the industry, how the technology is evaluating to the industry standards. Okay, so if you see in the logic technology, uh, there are so many foundries. What this foundry? The foundries are nothing but they are designing the chips. You know that, right? IC integrated chips. So in the industry, there are so many foundries: global foundry, TSMC foundry, and also America. There will be two more foundries, but worldwide we are using the TSMC. Why are we using the TSMC? Because TSMC is the high throughput. We know that throughput, right? Throughput is nothing but the if you are having the 100 chips. So if you are manufacturing the 100 chips, out of the 100, 95 chips are successful through this TSMC technology. So what the TSMC will do? The TSMC will give the rule deck files for our design. So you know the process of IC chip design, right? So we are lithography. After lithography, they are designing the metals. After that metals, so after poly, everything those are steps we already know that. Okay, so in the TSMC, so if you see the era of this logic technology, there will be Moore law, right? Everyone knows that Moore law. According to the Moore law, for every 14 to 18 months, the number of transistors will be doubled. or the area is of the industry. So of the how it is often. So let us consider on CMOS. Here it is source, here it is drain, and this is the gate. So what the technology is nothing but this is the channel length, right? So this length is nothing but the technology. If it is 130 nanometers, this is 130 nanometer technology. This is source, drain, and this is gate. Okay, if this is 130 nanometers, this is 130 nanometer. If the distance between source and drain, nothing but the channel gate length. If the gate length is decreasing, the technology is changing. 130 to 180 nanometer, what you are saying here, right? This 130 nanometers, this 3 micrometers is nothing but the 300 nanometers, later than 210 nanometers, 180 nanometers, 130 nanometers. Right now, what we are working on, it is under 3 nanometer. Okay, so we are coming from the 300 nanometers to 3 nanometer right now. We can assume the 3 nanometer how much it says. It is very minute. So that much of chips we are designing over here. Okay, so right now you are coming to the how the technology vary from here to here. Is there any scaling? Yes. In the industry, uh, till 45 nanometers, there is a scaling factor. If you see the area, it is equal to length into width, right? So if I decrease the length is 0.7 and width is also 0.7, the area is nearly equal to half of the area, right? So So in the industry, if you see the first technology, it is 300 nanometers. So after that, it is 210 nanometers. So the shrinking is coming from the 300, 210, later that 180, later that 130, later that 90 nanometers. Like the technology is varying from one technology to another technology. So what are the challenges from 300 nanometers to 300 nanometers? Let us discuss later. So before that, let us discuss about FEGA and ASICs. So what I am explaining everything is related to ASIC, right? So then what about FPGA? Okay, in the field programmable gate array, we know that Xilinx is provided in the FPGAs. Those are with SRAMs. SRAMs is nothing but the RAMs, memories. So if you see the, this is, let us consider this is one of the chip. So in this we have the block memory and logic cells. Okay, this SRAM is provided by the FPGA. If coming to the FPGA, those are field programmable gate arrays. So what are the advantages over the FPGA? So actually in the industry or whatever in the theoretical you learn in the education also, we are dealing with the FPGAs, right? Raspberry Pi ports, all those is comes under FPGA. In that FPGA, you can write the data, you can read the data, and you can execute the data, you can erase the data. So that is the advantage of FPGA. So what will be the use? So it is low cost. You can design the multiple programs on single FPGA, one after other. So it is lowest cost, and as it is also low volume. And also the non-recurring engineering cost is also less in FPGA. If you consider the one FPGA, we can use one FPGA board to many applications, right? So that is better advantage. And also this is standard. So if you consider the Raspberry Pi board, that is only one particular product. We can use that line. We can use it as a line indicator, and also where we can already we have workshops, right? In our GMR also, when I'm studying, there will be workshops. So they are using the Raspberry Pi boards. So those are only FPGA boards. So the Xilinx what they provided, there are so many FPGA boards. Those are IPs. So, okay, if the FPGA is good, why you are coming to the ASIC? So, in the FPGA, the disadvantage is slower performance. So, those are only for lower applications you can use. For high-end applications, you cannot use the FPGA, right? And also, size is also limited to the 25 million systems gates, and this is digital only. There will be no analog in FPGAs. So there will be analog to digital converters, and also there will be digital to analog converters. All those are not with the FPGAs. It is not possible with the FPGAs. So these are the disadvantages. So let us see the difference between FPGA and ASIC. So FPGA is simple, but it is not long runtime. Okay, and also uh, it is a time to market product. What is this time to product? So if I consider one chip, nearly what we are designing the chips, it nearly takes 1 year to design for us only. Actually, I am the PD engineer. So in the chip designing, I am the backend designer. There will be front end also. So if you want to design a chip, it takes nearly 1 year to us. So from only 1 year to us only. So if it is taking 1 year, so if it is come to the market, it will take 2 more years. So nearly it is 3 years. So if we consider FPGA, there is no much of time. This is nearly less than 1 year. So this is the faster time to market product. But when come to the ASIC, it is longer runtime, as I said earlier, and also speed is also slower. So these are FPGAs using the normal applications, right? So those are slower, and also ASICs are fast. So what you are using in our mobiles or in our microprocessors, and also what we are using in the motherboard, all those are comes under ASICs only. So these are designing is longer runtimes. So when you see the mobile, in every 1 year we are getting the new mobile. So it is thin and thick, from thick to thin. So what it is possible, these are through ASICs only. So the turnaround time is more, and also the reusability. If we consider the FPGA, we can reusable, right? And also it is flexible. When you consider in the ASIC, it is not reusable. We can design only ASIC for a single purpose only. So if you want to use and learn to digital converter, that is only for A to D converter. You can't use for other purpose. So it is not flexible. And also wastage is unavailable in FPGA. Why? Because you can erase the data, we can execute the data, we can use for other purpose. But there is no wastage of hardware. So hardware is only particular for ASIC only. And also, so if you consider FPGA, if their number is less, then FPGA best. If you consider the ASICs, it is large in number, then it is better. So particularly if I said which one is should you choose, it is depend on the area, timing, and power constraints. So depend on the technology and depending on the uses and depending on the speed, depending on the market, everything we can choose the what is better. Okay. So that's why coming to the FPGA, we are came to ASIC flow. Okay. Okay. In the ASIC, what we are using, ASIC is the mature process. It is silicon proven process. What is the silicon proven process is? So if actually what the manufacturers will do is they actually take the silicon dioxide, nothing but sand. They take the silicon dioxide and then deoxidize as silicon from they differentiate silicon, and they what they do is they form a vapor. So there will be zygote, and also they divided the total zygote into the vapors, single vapors, silicon vapors. On that silicon vapor, what they will do is, so they form the oxidation, metallization, lithography. Through all the process, the ASICs will design. Okay, so if you consider that design, it takes so much of cost. So if that much of cost, you can't waste that ASIC chip. So that's why it is ASIC takes more time, and also it is the uh, very costly. Okay, so what we are explaining here is I am explaining the what how the ASIC design flow will do here in industry. Okay, so so we have to choose the ASIC design flow. Initially, let us consider there will be some steps. This is oral. In this chip design specification, there will be architectural design team. There will be so many teams who are involving the industry. So where I am in industries, I am the PNR engineer. So these steps are divided by different engineers. Yeah, that is concerned. Uh, First, what the ASIC design cycle? This is the overall ASIC design cycle from starting to ending. So, in the let us consider one example. I want to design a one gate. Like I have two houses. So when the two houses are using the one motor, so at the time only motor on one at a time. So what will have? So let us switch off the motor for one house when the second house is using. So like that we're using the gates, right? We know the XOR gate and XNOR gates. So that is one simple example. Like that. So if we want to consider the any specification, so right now what we are working on, we are working for the ISRO and also AMD teams. So AMD processor, you know that, right? The MA200 processor, and also there will be an AV33 processors. We are working on that. So the team in the top level, what will they do is there will be chip specification. So the main thing is what they will do is they consider why the chip we have to use. So initially they design the specification. So now also there will be some constraints, the area, timing, and power. So in the specification, the hardware and software requirements. So to set up the hardware, how much cost required, the microarchitecture, and the how the functionality. If it is a low power technology, they will use the low power technology, and it should be work as a high speed. They should use the high speed, and also if that is power on, means some terminals. Actually, in the some devices, when you are using the power, then only the power should be used. Otherwise, the power will be wasted, right? So at that time, you have to use the power specification process, and also area. Area also should be less. And so by considering all these aspects, we are designing the chips. So and also, what are the teams are involving when chip specification is designing? So actually, there will be two teams available at the chip specification. The design team. The design team will generate the RTL code, and the verification team generates the test bench. I will discuss the RTL code and test bench in later steps. Okay. In the design entry or function verification, what they will do is, so actually, when in our programs we are designing the HDL, right? So there will be HDL code, Verilog and VHL. When we are using the Verilog code, we write the code, and also after coding the after write the code, we are dumping the code into the we are testing the code with the test vectors, like we are giving the simulations like 0 and 1, some functions. So like that only here also they are checking the code, how the code is. So once the code is ready, they give that code to the simulation purpose. In the simulations, what they will do is they perform the test vector performances. In that, actually, they will check the uh, coverage, how the code is working. So if the code is working without any errors, if it is 95% coverage, it is best. Otherwise, they will don't go to the later stages. This is first and foremost test. So why? Because if it is designed till last stage, if there is no issue, if there is any issue, can't do anything, right? That is in millions of crores. So that's why at the first step, what they will do is they take the code and they will design the test vectors, and they will to check the coverage. So if everything is okay, then only they will inform to the next team. So there will be different tools, functional simulation tools and timeline simulation tools to verify the circuit designs or test benches. So right now, what we are coming to here is synthesis. Okay, in synthesis, actually what we'll do is, uh, so now I want to design a simple gate like some inverter. If you want to design inverter, there will be some input, right? And also some output. So if I want to connect this inverter to the another gate like mux, so here is the net, this is the cell. So first there will be some delays, and also if I consider, there will be sequential cells. These are the combination cells, these are the sequential cells. So for every sequential cells, there will be a clock, right? So this is clock. So in this designing, what we have cell delays and also net delays and also clock also. So we are working on these things. So the data launched by one sequential design reach to the this sequential cell within less time, nothing but within given frequency. So that is our main advantage. That is the main aim. So in this, we need to consider all those things. So you need to consider these cell delays, these net delays, and also in the weather conditions. Due to the weather conditions, also there will be changes. If you consider the area, timing, and power, those are the main aspects. The area should be less, so we can accommodate all the cells in a single chip within less time. And also the dial should be reached from here to here within less time. Nothing but high frequency. It should work as a high frequency, and also power. The power should be less, the power consumption should be less, then only it is the better design. So what you have to do is the first initially, let us consider these are the cells. Okay, so we consider these cells in the synthesis. What we will do is in the sense is we are converting the RTL code to the gate level netlist. So the RTL code we know that, right? We'll write the behavioral model or any model. From Verilog code, we need to generate the synthesis. Synthesis is nothing but the converting RTL code to gate level netlist. So the code is converted to the gate level netlist. That is the synthesis. So when you're converting the gate level netlist, you need to take the library. Why the library? Actually, in the libraries, actually there will be so many files need to take as the input. The library, left, and also cap tables. What those all this contains? The library is nothing but in that in that library we have the cell delays. Actually, I shown that one image, right? In that the cell delay should be presented. So the cell delay came from the library, and also the area, how much the cell area, that is also come from the library. And also there will be so many libraries. If we consider standard cell, that is standard cell library, and also if we consider the macros, there will be macro libraries. So for every cells there will be some libraries. So that is the library. And also depending on the temperature, and also depending on the voltage also, there will be so many libraries. Let us consider the voltage is 1 volt is the optimum voltage. So if you consider every cell need to get the 1 voltage to trigger from 0 to 1 volt, or to recharge from 1 to 1 to 0 volts. So the input should reach, it should be get 1 volt, right? So that is that optimal conditions. But in the real life there will be no one, right? Either it will be 0.9 volts or it will be 1.1 volts. So what we are doing is we are taking so many conditions, like the 1 volt condition, and also 0.9 volt condition, and also we are taking the 1.1 volt condition. That is respect to the voltage. If we consider the temperature should be vary, right? It should be 0 degree centigrade, it should be 100 degree centigrade, or it will be 200 degree centigrade at junction temperature, right? The junction temperature is very high. So according to that also we are considering the libraries. So in the libraries we will take the temperature and also voltage as the reference. So by considering those we will generate the libraries. The libraries also inputs to the this census. So once we get the census, so we have the library and also we have the netlist. The netlist is nothing but the RTL code. So once ready, and also what we need. So here already we get the cell days from the library, and also the cell information, and also net delay. The net delays also came from the libraries, and also the net information where it come from the left. The left is nothing but the layer information at exchange format. In this lab, actually we have so many layers. There will be stack M1 to M13, like metal 1, metal 2, metal 3, metal 4. Those are having different capacitance. I will discuss tomorrow, day after tomorrow, about the routing technology. So right now, let us assume there will be so many routing layers. So every layer has different delays. So depending on the net delay, we need the net delay. So the cell is depend on the input transition and also output load. So in the library, what it indicates, there will be two parameters: input transition and output load. Based on this input transition output load, the cell will exhibit the different delays. If the input transition is less and output load also less, it will be less delay. If the input transition is more and output load is less, there will be some delay. So in the library, we have multiple. Actually, I don't want to show the libraries here. Actually, this is the confidential for the design what I am working. So that's why I'm telling the real scenarios. So if the input transition is more, the cell delay is more. The output load is more, the cell delay is more. So based on input transition output load, there will be so many libraries. That is the one of the aspect, one of the ratio, and also the footprint. If you the footprint is nothing but the, if you consider one cell AND gate, the AND gate we can use multiple times. So for every AND gate we have one footprint. So and also there will be drive strength. So if there is a low drive strength, it will drive less load. If it is more drive strength, it drives more load. So all those things are comes under library only. In the library files all these things existed. And also the left, in the left what will do, the width of the metal, the pitch of the metal, the spacing of the metal, all those comes under the metal layer. So if you consider these delays, and also here I am saying that clock, the clock information coming from the SDC. In the SDC is nothing but the synopsis design constraints. In the SDC, we are having the clock period. So how much period it will should work? If it is 1 gigahertz, let us consider 1 nanosecond is 1 gigahertz, like that. 1 megahertz is nothing but the 1 nanosecond like that. So 2 gigahertz, 3 gigahertz. If the frequency is more, the capability of the loading is the more. So that's why a different there will be different clocks with the different frequencies. So if I'm consider this is the functional mode. There will be scan mode also. I will explain in the DFT. There will be DFT. What they will do in the DFT. So there will be functional clock and also scan clocks. There will be different clocks over there. What is one is the low speed clock, one is the other speed clock. So these all comes under the SDC. So this is also one of the input to our design. So so once we get the SDC, we get the library, we get the HTL code, the RTL senses. Actually, real time there will be so many tools. Genesis compiler, RC compiler. Genesis from the synopsis, RC compiler is from the cadence. Actually, before saying that, there will be two companies. They provide the tools to industry, mainly cadence and synopsis. There will be different names for one other two other. So RC compiler is the ICC, the synopsis compiler, and Genesis is the from cadence team. So by using those, we will design the code from HTL to they will convert the code to the circuits. Okay. Once gate level netlist is ready. So once gate level netlist is ready, in that senses, what the other steps is there? In the synthesis, they translate the RTL code to the gate level netlist using logic synthesis tool. That means the timing constraints. As I said, the timing constraints is nothing but area, timing, and power. Once synthesized database is ready, it will goes to the DFT. Okay. So in the synthesis, and also there will be logic optimization also will do. The tools are mature right now. In the olden days, there will be no maturity of the tools. What they will do is, if there are two inverters, those are comes into the one buffer. Right now in the tools, what they are doing is they are optimizing the code. So in the olden days, there will be that much of maturity is not there. So in the olden days, instead of one buffer, they are using the two inverters. So this is the logic optimization. At the time of coding only, the optimization is done. And also there will be physical design and layout. So physical design comes under PNR. I will explain. So once netlist is ready, synthesis is done, we are going that synthesis netlist to the DFT team. Okay. What the DFT team is do before going to the DFT, what they will do is actually, if you consider the chip, it is the chip is having a more area. So in the industry, what we are doing is we are partitioning the chip. So let us consider we are calling it as tile. So there will be top level chip. So the top level chip is having so many instances. So what we are doing is we are dividing the total chip into the sub chips. Nothing but we are calling as tiles. So the total tile is converted into the we are partitioning the total tile into the multiple tiles. So what is the advantage over here? If we take the one as a chip, it will takes more time to run the whole design, and also multiple workers, multiple processors can't do anything. If we partition in the chip, multiple designers can design their chip, and you can integrate in later stage. Once the chip is ready, you can integrate the whole blocks as a single chip. So that is the advantage. So once the code is ready, what we are doing is we are converting the total chip into the multiple chips. That is one is the chip partitioning. In this, what you are following is hierarchy models. What is the hierarchy models? Actually, that is the top-down approach and bottom-up approach. So in the top-down approach, so the chip is going to the one hierarchy. If it is the less gate count, it is better the top-down. Why? Because so if you give single chip to the one person, it is simple design. There will be no issue. They can design in less time. They will be okay. That is top-down approach. But in the industry, what we are doing is we are dealing with the high modules. Nothing but the gate count for the single chip is more than 2 million. So the total chip is having the millions of millions. So that much of gates are there. So that's why we are designing the total chip into the multiple chips. We are assigning to the some other persons like some team. There will be different teams. Like if there is a unlocked to digital converter, that is one team. If there is a serial bit processing, there is one processor. So like that, we are depending the total chip into the multiple tiles. So that is the bottom-up approach you are following. In the bottom-up approach, what you are doing is at the bottom level. So if you consider the 10 chips, so one chip is designing their design, so other persons designing their chips. So once all the designs are completed, if they met the area, timing, and power, so what we are using, we are combining all the chips into single chip. So we are going with the bottom-up approach. That is the bottom-up. What I am talking is. So in the chip partitioning, what you are doing is, so we are considering the total chip into the single chip. So once done, we are dividing the total as functional blocks. Okay, and also once the design is complete, so we are distribute the total chips to the different people. So once done, what you are doing is the DFT. So what I am talking earlier is that is front end. This DFT also comes under front end. So in the front end, there will be front end designer like there will be logic design. Logic design comes under the coding. And also what this is DFT. Here, what the engineer work is DFT engineer. There will be so many engineers who are working. So I am the PNR engineer. My work is comes under DFT. So in this DFT, what they will do is if they consider the more chips, right? So they are performing the test vector. In the test vector, what they will do is, so the chip is given to the multiple tiles, right? So functionally you can perform later. Before that, we can test the designs by using the stitching. Like this is one flop, this is the combi logic, and they reveal some other flop. In the function, what will do? If it gives us some zero, that should be reach here, zero, right? Through all this combination logic, but it takes more time, right? So perform the operation, it will take more times. So in the DFT, what they will do is the combination is okay, but sequentially is having more cost. So what they will do is actually there will be so many inputs over here. Some like this is the D, this is the Q. So there will be SA scan, and also there will be SQ output. So earlier I said there will be so many clocks, functional clock and scan clock. In this scan clock, what they are giving, one clock they provide to the scan input. So they are not giving any input to the D. This is functional. They don't touch DFT. So in this, they giving the scan input to this input, and also they perform the test vectors from here to this scan output to again this scan input. So they're excluding this logic. They're not taking this logic. They perform the scan stitching, nothing but one output to this flop to another flop. So the flops are in parallel. So like that, they give the text vectors. There will be so many operations. So they given the one input here. They are taking the one output here. If that is reached in the within time, that is good. If they are giving zero here, if they are getting one here, there will be some bug. So what they will do is they are going to the backtrace. They will check here. If this is one, so it is a fault. Then here only they will check. So this is the default. If they are getting zero here, this is okay. This is default. Like that, they test the functionality, the DFT. The DFT team is checking like that. In this, so it different stages. So what they are telling is, once the chip is ready, if it did not test the vector in the last minute, it will be very worst case. There will be so much of cost. That's why they are testing the at TFT by giving some frequency. So in this, there will be different logics. One is scan path insertion, what I said. So in this scan path insertion, what they will do is they link all the registers into one long shift registers. You know the scan shift register, right? If you give the zero, it will shift to one flop to the other flop. Like that, in this also, they're combining all flops in a parallel manner, and they give the one input and they will generate the one other input. So they check the smart part of the design instead of whole design in one go. This is scan path insertion. Okay. After that, there will be memory based. This is nothing but built-in self-test. So if it goes to the lower technology node, if the flop is okay, if you consider the memory, it takes more area. For that, whatever they do is they perform the MBIST. So in the MBIST device, what they use is check the RAMs. So instead of standard cells, instead of either flops or latches, whatever it may be, they're checking the SRAMs. It is a comprehensive solution for memory testing. So this is one of the technology. So what they will do is here. So here let us consider one flop is here. Here one SRAM. SRAM is nothing but the memory. This memory has having the more area. So there will be so many flops also exist here. This is one of the memory. This is one of the memory. This is one of the memory. So one of the RAM. I mean this one RAM. There will be so many flops over here. So this is one of the block. This block also gives to the as a one level. So in this what they will do is there will be some pin over here. So they are checking the SRAMs over here. If you can say SRAMs, they are checking all the SRAMs through ambushed mode. So this is one of the technology. Once memory bit also done, there will be ATPG. What the ATP is? Automatic test pattern generation. In this is the simple and easy what the present designers are following. In this, they are generating the test vectors or sequential input patterns to check the design for faults, as I explained here, right? So they will take the one flop here and one flop here. So whatever it may be in the placement, the flop may be here also. If one flop is here, another flop is here. In the placement, once placement is done, if the flop is here, they did not check the placement, just they stitch the scan. There will be chain over there. We are calling it scan chain. They are taking any nearby flops, they stitch the scan, they give the inputs here, they take the outputs here. This is nothing but the automated test vector generation. And thus they give the suggest sequence 1 0 0 like 1 0. Let us assume this sequence. So they give the 0 here first. And also this is in one cycle. After one cycle, they will give second cycle like that. You know the cycle, right? If I consider one flop here, if I consider another flop here, this is clock and this is clock. This is the clock input. So what we'll do is this is launch flop. This is capture flop. We are giving the data here. We are taking the data here. So if you can say launch here, if you can say capture here, the data launched by the launching it should be captured here. That is within one cycle. Let us consider one NS. So in one NS, the data should be reached here from launch to capture. This is the if for every flop we are checking here. So this is the clock generation. So from launch to capture, it will take one clock period. If the data, let us consider this is the 10 ns. Clock is 10 ns. So let us consider there will be combo delay. This delay is 1 ns. This delay is 1 ns. This delay 8 ns. So the data launched here 1 plus 8 plus 1 10. So the data launched here should be captured here. It should be okay. Then there will be no problem. But if the combination delay is 10 nanoseconds, what is the problem? 1 plus 10 plus 1, it is 12. But the availability is 10 nanos. So this is not possible. In this case, what we are doing is we are doing the PNR. What we are doing, this is the PNR, what we are doing. In this case, what will it do? If there is less, if there is more, what we are doing is comes under PNR. So once the DFT is done, before going to floor planning, uh, in the synthesis, once synthesis is done, actually we are giving the synthesizer netlist to the there will be there is static timing analysis team. What they will do is they will check the design. So if the design is met for as per the timing, so as I said, if it is reached the 1 ns, there will be no problem. It is more than 10 ns, that is the problem. They will check that. So okay, so in the synthesis there will be it is not physical, right? It is nothing but logical. So if you are considering, you are saying that logical senses, but in the real time, is it good? No. Why? Because there will be assumption only. In the senses, there will be no nets. There will be only cells existed, but it is not placed, right? So it is only logical. So what is the problem over here? We get the uncertainty. So even you are getting the 10 NS, there will be some uncertainty. So missing out due to the net delays. Okay, cell delays. There will be no cell delays, real cell delays. There will be no net delays, and I mean there will be no real cell delays and net delays. So if you consider the 10 NS, under 1.5 NS came to the uncertainty. So that is nothing but 15%. In that 15%, what you assume is due to the cell delays and net delays, 10% is gone, 15% is gone. The remaining 5% is due to the cross-talk. That cross-talk is nothing but the signal noise. Through the noise, you get the delays. That I will also explain in day after tomorrow. And also OCV, on-chip variation. When the chip is in the operation, due to the due to the temperature and voltage, there will be some drawback of voltage. That is by considering there will be skew in nothing but there will be no clock, right? In the logical senses we are just giving applying the clock, but it is zero. There will be no clock delays till the placement. Till the CTS there will be no clock delays, only logic delays. So by considering all this, what we will assume is that is overall 20%. If you get the 10 NS, overall 2 NS is uncertainty. So the data should be reached from launch to capture within 8 NS only. Real it should be 10 NS, but by considering the uncertainty, it should reach in 8 NS. So that is the target. That is comes under census. So once the data is going to the STA team, they will check all those things. If the data is coming to within time or no time, it is taking more delay or less delay, and also there will be input delays and output delays also. If you consider there will be ports and pins. You know the difference between pins and ports, right? If you consider a chip, within the chip, there will be so many cells. If the cells having different pins, the cells have the pins, but the chip is having the ports. So for every port, there will be so many delays. By considering all those things, the STA team will generate the delays and they provide as HDF to census team. So if the design is not good, so the census team what will they do is they remove the logic or what let us consider. As I said, 8 NS. 8 NS also it is possible. Let us consider 6 NS. 8 NS is if there is exist. So what they will do is they will reduce the logic here, one of the logic, or they will optimize the logic. But if they will don't want some other any flop or any latch, they will remove that. So based on their performance, we will get the sensation at least, perfect sensation at least. Okay, this once census is done, as a PNR, we get the synthesized correct physical sensation at least. What is physical sensation at least? Once the census is done, there will be some tools over there. They assume the cells over here will exist in this place. So they assume the tool is aware of that. So let us consider some cell is here, some cell is here. So they perform the physical census. Once the physical census is done, we get the delays, but those are not real delays. But compared to normal census, physical census is better. So after once physical census is done, the placement of the the assumption of cells existence is comes under the physical census. Once done, we get the census in at least. This is step what we are doing here. So once we get the census in at least, we are doing the floor planning. Okay, what is this floor planning? So once DFT is done, physical implementation is done. So what where I am working is from here to end of the chip designing. From floor planning, we are working here. So the first step is RTL to GDS. This is the floor planning. In this floor planning, what we will do is we are the placing blocks in the chip. So nothing but let us consider. I got the one. As I said, there will be so many tiles. If I get the one tile here, let us consider this is the one tile. This is the core. Okay. So what we will do is we have so many memories. Those are placed here. One memory, two memories, three memories. Let us consider four memories only as a simple purpose. So here there will be ports. So these ports are talking to the some other models. As we divide the total chip into the multiple chips, right? So here maybe some other chip. Here is a port. There will be a connection. So in this connection, so let us ask if we divide the total chip into the multiple chips, from this connection to this connection there will be delay. Yes, there will be delay. So that's why what we are doing is that there will be time budgeting. In the time budgeting, what we will do is, let us consider one port here, some other port here. If we consider the total delay is 100%, we are divide 33% to this port and 33% is to this port and remaining percentage to the this ports. So we are constraining here. We are assuming this delays also. So while we are designing the chip, let us we have to consider all those things. Then only it is perfect design. Otherwise, that is the thing. So we are considering these delays also. So once we get the floor plan, so there will be modules. We are calling as modules. So this is RAM. This is RAM 1. This is RAM 2. So in the floor plan, what we will do is this RAM 1, there will be a flow line connection. What will there will be some settings over in tools. So by enabling those settings, we are checking this RAM. When we click this RAM, it will talk to some other ports over here or here. It will talk to some other ports. So initially what we are doing is we are placing this memory to here. Why here? This is optimum to this and this. If this is talking to these ports and this ports. If it is this talking to this ports and this ports, we are placing here, but not in the middle. This is restricted. Why? Actually, the memory is nothing the power hungry element. If you place the memory in the middle of the chip or in middle of the core, it takes more voltage. If it takes more voltage, there will be more power consumption. So it did not get the sufficient voltage. Why? Because the standard cells are less area, but the memories are having more area. So that's why you are not placing the total memory over here. You are placing memories in edges. Like here, I will show you the floor plan. So if we consider the floor plan, these are the memories, these are the ports. So this is one model, this is one model, this is one modules. So we are placing the memory and also we give the some space in middle of the chip. Okay. So how can you, is there any guidelines for floor plan? Yes, there will be more guidelines. For one technology, there will be for one technology to one technology, the rules are varying. If we consider the TSMC, right now we are working on 3 nanometer technology. There will be 6 nanometers. Actually, I work on 180 nanometers and also 24 nanometers, 21 nanometers, and also 7 nanometers, 6 nanometers, 5 nanometers. Right now, I am working on 3 nanometer. So from technology to technology, there will be so many rules. So based on those rules, the TSMC foundry who manufacturing the chips, they have some design rules. They give the design rules to us. So based on those rules, we are placing the these macros. So I said that if I consider this macro, why can't we place these macros here to here? Yes, we can place. But the problem is these macros can talk to these macros. So these are the group of macros. While placing the macros initially, we are following the flow lines. So flow lines, based on the flow lines, we are placing the these macros near to these ports. So once the ports connection done, so we can choose this macro. By clicking on that macro, we can get the irrespective to any macro talking to this macro. So we are placing those macros here. So there will be so many models. Some so as I thought is a analog model, or digital model like that. So we are placing yes these all the one model related macros to here, and these macros related modules to here. So we are placing those macros here. These tracking macros here. So like that we are placing around the core. Once this is the floor planning. So while doing the floor planning, we will follow the so many rules. Actually, if we place the macros, if we place the macros, let us assume one macro here, one macro here, one macro here, one macro here. These are the pins. These are the macro pins. If this macro talking to this macro, if this macro is talking to this macro, this is worst floor plan. Why? There will be a crisscross connection. So it takes more delays. The net is routed from here to here. So instead of what we will do is place the macros here. So we are moving these macros to here, this macro to here. Then the connection is less. So we need to place the macros as an optimum place. This is the one of the floor plan. This is like that. There will be so many rules. There will be hundreds of rules over there. There will be some min placement, and also this macro should be aligned to this macro row. The rows and rows, right? So if we check the chip, the total chip is divided into the multiple rows. So what we are doing is we can place the one cell here. So every cell has two power steps, right? A voltage, power and ground. So in this what we'll do is this cell power is aligned with this track. This cell is aligned with this ground. So we are talking as this is the uh, so this is one of the cell. So this VDD is connected to this VSS. This VSS is connected. This VDD. They're checking with the VDD. These are called as follow pins. We are called it as follow pins. So in the industry, these follow pins are from top to bottom like the follow pins. So every follow pin should combine two cells. So this VDD and this VDD near to here, and this VSS should be here. This VSS should be here. So by this we can save the place. So one of the advantage like that the follow pins are adjusted. These follow pins will have the layer of M0. This is the M0 power supply. All the follow pins have M0 power supply. Okay, and also there will be so many layers. I will explain in the power plan. So in the floor plan, we are placing the macros like this by without any wastage of memory, wastage of area, wastage of routing availability. So once floor plan is done, this is the good floor plan. So it should be minimize the total chip area. If you consider the total area while doing the floor plan, it should be minimized. And also route based DZ. I mean what I said right now, right? It is routable. And also it should be improved signal delays. Means if you have less signals nets, it is less delay. If you have more delays, more signal net lengths, it is more delay. That's why the main step in the PNR is floor planning. Okay. Once floor plan is done, in the placement after floor plan we come to the placement. In the placement what you are doing is it is the placing of standard cells in a row. Okay, and also placement requires large area and also degrades performance. So if you see the placement here, this is good placement, this is bad placement. Why? Because this is less nets, these are more area. So in the placement what you will check. So in the chip, if the standard cells are placed here, here like that. So all the standard cells are placed here. In the placement, what we'll do is we can place the standard cells. There will be tools also. What you're doing in PNR tools, so there will be ICC tools over there. ICC is from Synopsys, and from Cadence there will be tools. Innovest tool is from Cadence. So these are the tool names. The ICC is from the Synopsys, and also Cadence from the Innovest. So right now we are using the ICC tools. So in the ICC tool, what it do is after floor planning, it will place the standard cells. The tool is just placing the standard cells. If you can say this is one row, the standard cell may place here, here. So as I said, there will be so many models. One model of standard cells place here, one model of standard cells place here. So like that, there will be so much of placement here. So in the placement, what are the issues you need to face? What you have to overcome those? So those let us consider in the mostly after placement, we need to check the congestion and timing. Okay, before the placement, if we get the design, we need to check the check design. In the design, what we do is, so let us consider 8-bit multiplexer. If you design the 8-bit multiplexer with two 4x4 multiplexers, so what you need is in the HDL code, two 4x4 multiplexers. I mean nothing but we can define the one 4x4 multiplexer, and we can use that 4-bit multiplexer to the remaining two. Like we are designing the 8-bit multiplexers. So in the check design, what you are checking is if you write the code. If just you are giving the 8-bit multiplexer, just you are defining the 4-bit multiplexer, but you didn't get include the 4-bit multiplexers. The tool is using the 4-bit multiplexers, but you are not defining the 4-bit multiplexer. That is the drawback, right? That is one of the check we are checking. That is nothing but the check design. That is comes under the check design. That is nothing but the check black box. What we are coding as it is black box. Black box is nothing but the there will be definition of the module, but you are not write the code for that module. That is black box. Okay. And another thing is empty modules. In the empty models, what we will do is, so you write the 4x4 multiplexer also. But in the 4x4 multiplexer, just you define the input connection and output connection. But you did not given the sequence, like the output is in XOR of 1 or 2, like that we need to write, right? So if you miss that code, that is empty module. So in the initial stage, after getting the synthesizer netlist, before floor plan, we will check the check design. In the check design, just we are checking the any black boxes and empty models. That is one of the major step before the placement. So one thing, and also after the check design, check timing. In the check timing, what we'll do is, so as I said, every flop should get clock, right? So if you define the flop, it should get the clock. Without clock, it should not perform any operation. So what you are checking is every flop as clock. If any flop did not get clock, first we have to inform to the top level team. So we need to inform the top level team. So this flop did not get any clock. So they will provide the clock. And also any input delays or output delays. Why? Because input delays or output delays. So if you consider the design, let us consider chip here. In this, one flop is here. This is comes on here. It goes to here. This is the input port, and this is the output port. So there will be some clock here. We have the clock right in the chip, but for input ports, output ports, where will be the clock? These are the outside of the our chip, right? So in this design, what we are assuming is we are defining the virtual clocks here. In the virtual clocks, what we are doing is we are considering the same clock period of this to here. So we are considering the clock period virtual clock. The virtual clock is nothing but the it doesn't have any ports. So we are defining the virtual clocks on this input. So like there will be no input. If you consider this clock has port. There will be CPL F clock port. F clock port has a one clock. The scan clock has a one port. But there will be no clock ports for this input or output ports. So what we are doing is, so we are defining the virtual clocks and we are giving the clock period of this clock to this, and also we are generating the path. Instead of input to output, we are defining the total as a three paths: input to flop, and flop to output, and also input to output. These three we are considering. So these three also should be follow. This is the target. So that's why the piano is very critical compared to all other designings. We need to match all the clock period from here to here. Everything you need to follow, and you need to get the target. We need to fix those. So if you miss the input delay here, this input delay has some delay. If you miss that input delay, why? Because this is not the good right. So some other flop from other design will reach to here. So the timing will be violate here. So this input delay, the every port should have delay. So we are checking the input delays or output delays for this check timing, and also we are checking the min pulse width. In the min pulse width is nothing but the actually what we will do is, if we have this rise and fall, this is overall clock period. This is not good, right? Why? Because this is having less pulse. This is having more width. So in the check timing, we are also checking this also. The clock should be having the equal rise and fall widths. So if it is having the any minimum pulse width, we will need to inform to the top level team. So why? Because if the let us consider one capacitance charging. If we having the less rising width, it will charge to, if let us consider 5 volts here. If you having less width, it will charge to only 3 volts, but it's not up to 5 volts, right? So this is drawback. So the capacitance should reach to 5 volts, and also it should reach to 0 volts. So they should be equal rise and fall widths. That is, we are taking as the min pulse, and also multiple clocks racing for one clock port. So what is that? If this port is having multiple clocks, I have slow clock and also I have fast clock. So if the fast clock and slow clock and depend on one clock port, that is not good, right? Why? Because the port should not know. It should work on low frequency or high frequency. It doesn't know, right? So that's why the port should have uh, the there will be only one clock for one port. That is also like that. And also clock not react to the plop, not reach to the plop. As I said, every plop have uh, one clock. And also, yeah, the port is not defined. If you define, actually we have the output here, so but not port is not defining here, so there is also problem. So by considering the synthesis, we have, after synthesis we will have the inputs as def. One is def, one is the netlist, and HDC and lips, lefts, all these are the inputs. So the netlist is nothing but the logical connection. What you are getting from the senses, it is logical. From input to output, so the logical it is coming. Okay, it is okay. But physically you need to write. So that should be in physical form, nothing but def. In the def, what you have is initially we have ports as I shown in the floor plan. Ports. So the ports and logical connection is adjusted. Once the placement is done, stencils are displayed here, like that. Initially, those stencils are at center only. So, so need to check the these things, and also there will be unresolved reference. That is the main thing. What is this unresolved reference? Actually, logically there will be connection in the netlist, but physically there will be no connection. What is nothing but, so logically you have the connection, you write the code, you have the connection from one flop to another flop, but physically on the def I did not get that flop. And also in logically you have defined one macro, but physically there will be no macro here. So all this comes under unresolved references. So we need to check this also. So while checking this unresolved references also, we need to inform to the top level team, array, we have the one macro here, but we did not get the macro in depth. So all of this we need to inform to the top level team. So these all are the basic steps. So okay, once done, floor plan is done. Okay. After floor planning, before going to the placement, there will be power planning. Okay. In the power planning, what we are doing is, before going to the place where power planning is done, in the power planning, if I consider this is the whole chip, in this is the core boundary, this is the chip boundary. From chip boundary to core boundary, some space should be there. Why? Because this other chip and this chip should not align, right? If those are aligned, the metal should be connected from continuity. There will be continuity. So there will be should not any continuity, and that's why we are giving some space over here. And also this is the core area. What you're using? This is the rails, nothing but power rails. These are the ring width and ring spacing, and also power layers. Actually, what you're using the, if you have 10 layers, for the power layers, we are using the top layers. Why? Because the top layers are having high width and high spacing. Why? If you consider the R is rho L by A, we know that rho L by A, right? A is nothing but width into thickness. So if we having less width, the resistance is more. If the resistance is more, it achieves more power. It takes more power. Then there will be more delays. So that's why the power mesh. While we design the power mesh, we are designing the power in the higher layers. In the higher layers, it is having the more width and more spacing. If it is having the more width, it is having the less resistance. If it is having the less resistance, it is having the less delay. And also the spacing is also should be more. Why should be more? If the spacing is less, the coupling capacitance is less. If the coupling capacitance is less, the delay is less. The delay is more. Okay. So if the so C is nothing but FA by D, right? The separation is more, the capacitance is less. If the capacitance is less, the delay is less also less. Why? Because that is nothing but the output load. Load is nothing but the capacitance. So there will be less capacitance. So that's why what we are doing is, if we consider the power, we are getting the top layers. We are designing the power in the top layers. So once we define the power in the top layers, the top layer power goes to these standard cells initially. So how the standard cells will get the power? every standard cells have VDD and VSS. That VDD has and VSS are in the lower layers, M0. If these are also in the higher layers, the chip is not enough, right? The chip should be less. So what you're checking is the the lower layers in the follow pins. Actually, I draw the follow pin right in the layer. The follow pin should be less in the lower layers. So what you are doing is you are creating a one mesh. One mesh is nothing but the from top layers to bottom layers there will be via stack. If I consider the 10 is the top layer, M1 is the bottom layer. From 10 to 9 one via, 9 to 8 one another via, 8 to 7 another via. Like that we have via stack. From that to M1 we are getting the power to the polar pins. From polar pins to the standards the power is going. So like that we are getting the power. Okay, for standard cells it will be okay. Those are small in area. But for macro, what we will do? Macro is the power angle cells. Why? Because those are high area. So for macros, what we are doing is in the power planning, we are having the rings. So these rings also having the highest, like not M10 but M6 or M7. So that M10 comes to the M6 or M7 through via stack. So like that we are getting the power from top layer to here, like this. And also what is these are the power pads. So the power pads are nothing but the then the chip we are giving one power to the all the power pads. So the power pads will convert the, so actually what you are dealing with the digital, right? But in the chip, uh, just a minute. So I am talking with one chip, but in the top level there will be so many chips. So these are the nets. So in the this is comes under digital. There will be no inductance effect in the chip area. Why? Because the rate of change of current is very less in the chip. But this is digital. But while you can say the total chips, the power what are the connections from here to here having the more length. So if it is having the more length, there will be inductance effect. So so what we are doing is we are converting the this. So if there is more, then we have to have the more voltage. So at the top level, we are applying the more voltage here, like 10 volts or whatever maybe. Just let us assume for 10 volts or 220 volts, whatever it may be. Here it should be 5 volts. Okay. So this 220 volts, how the 5 volts it should be? There will be some converters, analog to digital converters or nothing but the voltage shifters. So the voltage shifter is converting the high level voltage the low level voltage. So if you get the how that they for that conversion we are having the power pads here. These are the power pads what I am talking right now. These power pads having the converters. Okay, these power pads what they do is these power pads what they do is they take the more voltage and will they give the less voltage to the these power shapes. These are the converting from high voltage to the low voltage. This is comes under power planning. Okay. So once power planning is done, so we need to check the opens and shorts initially before placing the standard cells. Why we need to check the opens and shorts? If we are giving the power to this RAM, so here VDD stripe and VSS stripe. So if there is open from here to here, so that is the drawback, right? So in that what you are checking is, so you need to check the LVS. We are calling it as a LVS. So LVS is nothing but layout versus schematic. In this, what you are designing, so need to check opens and shorts. If there will be open, we need to check that open and also need to make the connection. The short, what is short? If one layer and another layer comes under one short, so we need to divide. Let us, this is one net. If this is breaking to two nets, this is open. So the power what is coming from here to here, this is not going. So this need to check and you need to make the connection. This is open. What is short? One net is going here, one net is going here. Those are aligning here. So what is the drawback? This even irrespective to two nets, it is treating as one net. So this is also problem. The in this also we need to jogging. So if it is one layer, we need to jog to the another layer. I will explain the routing a day after tomorrow. This about the opens and shorts, what they can. So we are joining from one layer to other layer here. So it should be fixed like this. So need to uh, before placing there will be no any ports opens or shorts. This you will check in the power planning. Once power planning is done. So once power planning is done, okay. After power planning, what we will do is we are doing the physical cells. In the physical cells, so what I'm explaining, there will be no continuity from here to here. So one metal should not continue from one chip to other chip. So here what we are using is there will be boundary cells. We are using the end cap cells. End cap cells means they are the robust, nothing but if you are designing a cell, one chip cell, this is one cell, this is chip, this is other chip. This nets should not comes from here to out. So how can you use? We are using the end capsules. In this end capsules, what these cells are nothing but these are giving, they are just uh, discontinue the terminal from here to here net. So that it discontinues the net. This is one of the cell we are using in the physical cells. Nothing but after power planning, we are using the end capsules. One is the end capsules. One another is tap cell. What is the tap cell? Already we know that a latch up. Okay. So in the olden days, every cell has the LUP cell, tap cell. The tap cell, what it does is it divide the total resistance into the multiple resistance. Nothing but decrease the parallel connection. If you consider one net here, it takes more resistance. So if you divide the one resistance into the multiple resistance, that the voltage is there will be no current issue, right? The current is dividing here. So we are creating the less path. So already you know that there will be some connection from VDD to VSS. There will be latch up in our study. If it is considered VDD, it is VSS. If there is a connection from VDD to VSS, that it is the latch up. So to eliminate this latch up in the industry, we are using the tap cells. What? Hello? Is someone is talking? Hello? 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 Is anyone is talking?
No,
No,
sir.
sir.
No,
No,
sir.
sir. No, sir. You can carry on.
No, sir, you carry on, carry on.
Okay,
You can
thank you.
carry on, sir.
Okay.
Some
You can
syllabus
carry
has
on.
overlap, sir.
Oh, okay,
No
okay.
problem, no issues.
So in the study, what we'll learn from VD to VSS, there will be latch up problem. Already we seen in the study. So to eliminate that latch up in the olden days, what we will use is for every standard cell, we are using the tap cell here. It is inbuilt design. If you consider the 65 nanometer reboot technology, so it is okay if you consider the tap cell within the cell. But what is the problem? It occupies more area. So when you come into the lower technology, the area should be less. So in the current technology, what you are using there is the in the after floor planning also we are using the physical cells like tap cells. In the tap cells, what you are using is we are considering the total chip. So we are placing the tap cells here in every 60 microns like this. So like this in a row. This is one of the tab cell insertion in the latest lower technology nodes. So with this, what is the use? If we have any cell here, if it is any having latch up problem, it may share this cell and this cell. So the latch up is eliminating here for standard cells. For macros, the latch up should be inbuilt. Why? Because the macro is so much of height. It is if it is considered 65 micrometers, it may be more than 200 micrometers. So the tab cells should be inside the macros. So like this, we are placing the tab cells over here. This is the one of the physical cell, and also okay, everything is okay. Once chip is ready. So if I have the any bug, functional bug, then what we'll do? We can't do right anything, right? So for that purpose, we are using the spare cells. So spare cells is nothing but we are storing some cells like buffer, inverter, and flop. So here like this standard spare cells. So as like we are using the stepney in our cars. If the punctures happen at the time, what we will do? We are using the other tire. Like that also here also we are using the space cells. The space cells means they're not using at the time of designing. I mean at the time of operation. At the last minutes, if any flop or burst, how the flop is burst? Are you talking? At that time what I am talking is actually if you are designing any flop or cell, there will be etching, erosion, and also there will be metal connections. There will be burnt out. If the cell is burnt out, means if a metal is burnt out, there will be short. These two layers may connect. At the time the cell is not working right. The cell is don't use. So at that time what will is you can't go back. Why? Because this is the more cost and also turnaround time is more. At that time what we are using the spare cells. By considering those also at the time of initial stages only, we are using the spare cells. Okay, so uh, so all this comes under the placement. Okay, once power planning is done, so we came to placement. In the placement, what we will do is we will check the congestion and timing. Okay, what is this congestion? What is this timing? I will explain. If you consider chip here, the cells should be distributed like this. Then there will be no issue. Why? Because it will take some voltage, it will take some voltage, it will take some voltage. If it is not happen, if the all cells are grouped as a cluster, then that is issue, right? So these cells will not get the more power. If the cell should get one power, but if the cells are all under here, there will be more power drawback. So this is one of the drawback we are getting the in placement stage. If this placement is what we will do is we are distribute these cells to here, like we are using the blockages, placement blockages. In that placement blockages, actually we are telling the tool that spread the cell from here to here, here to here. We are giving area here. So we'll get the report, we'll get the image. After that image, by checking that image, we will check and give the tool that you can distribute the cells from here to here. That is nothing but nothing but you are decreasing the congestion. Once congestion is done, and also we check the timing. Once placement is done, once placement is done, we will check the timing. So this is the first step in timing. So after the timing is more, there will be so many issues. So let us consider if there will be more levels of logic. Levels of logic is nothing but this is one flap, this is one flap. So there will be so many cells right here from flop to flop. If these are cells are less, there will be no issue. If the cells are more, that is the levels of logic is more. So at that time, what you inform to the designer, array, you have more logic levels. So can you reduce that? If you did not reduce the logic levels, you can't match the design. So we need to inform to the designer. This is one of the check. Or some other cases, if the levels of logic are also less, or some other things, the macro delays may be more. These flops delays. At the time also, the lib actually they need to copy the one lib, but by mistake they will copy the other lib. So at that time also we get the more delays. So that time also we need to inform to the designer, we're having the more delay. With it also we didn't get the correct timing. So that is also one we have to inform to the top level team. So like that, there will be so many checks. So in the next we are checking. Just I am explaining just basic steps. This congestion and timing are the major steps in placement. So when the placement is done, at the placement stage, we did not touch the clock. So just we are checking only cells with a clock period, ideal clock, which we are checking the ideal clock. Ideal clock is nothing but the clock from clock port to the clock pin should reach in zero delay. So at the placement, just we are defining the one stage to one stage placement, play CTS like that. So at the placement stage, we are not checking the any clock. Okay, once placement is done, so everything is okay. Then we can go to the uh, so once placement is done, we are going to the timing. Just a minute. Once placement is done, we will go to the CTS. In the CTS, what we are checking is the main is nothing but the clock responses. We are checking for the latency and skew. What is this latency? The latency is nothing but the from clock port to the clock pin. What is the delay? That is nothing but latency. If it is to launch flop, it is launch latency. If it is to the capture flop, it is the capture latency. So ideally, the latency should be equal. How? So if you consider chip, this cell should have the same delay. This cell have the same delay. So if the cell delays are if the latency is more, there will be skew. We are call it as skew. Skew is nothing but the capture latency minus loss latency. If this flop is having the more latency, if the flop is having the less latency, there will be so much of skew. So if the skew is more, the clock period also it reaches the out of the clock period. That is also drawback. So in this mainly we are checking the latency and skew at the time of CTS. Okay. So in this we are building the clock and also by defining the right in every stage we need to check the area, timing, power. These are the common things ATP. So once the CTS is done, we will check the all this latency and skew. The ILE should be skew should be zero. Nothing but the launch latency and the capture latency should reach at a time from clock port to the clock pin. So ideally should be zero, but in real time it should not be. So we are using multiple techniques, like we are building the clock tree, like H tree, and also fishbone, and also star tree. Like we are cross tree. We are using multiple techniques. So by using multiple techniques, we are decreasing that latency. So by decreasing the latency, also we get the minimum latency. So once the CTS is done, so latency is less, skew is less. Okay, this is good to the next step. So once CTS is done, we are going to the routing. In the routing, what you are doing is there will be global routing and detailed routing. So the global routing is nothing but the I will explain this is also day after tomorrow in routing algorithms. So in this routing, the global routing is nothing but the estimation. In detailed routing, it should be accurate. So by considering this routing, there will be route stage and opt-route stage and also reroute stage. Okay, everything is done. CTS is done, route is done, opt-route is done, reroute is done, everything is done. So uh, so routing is done. After designing, we will check the final verification. This is final verification where we came to here. This is nothing but physical verification. In this, we are checking the layout versus schematic. What is this LVS? LVS is nothing but the geometry and layout matches. So we are getting the netlist. What the netlist we are defining in the we are designing the in PNR that should be equal. What the layout versus the schematic is nothing but the logical connection, layout is nothing but the physical connection, those should be equal. That is one of the check. And also another thing is DRCs. We are checking the DRCs is nothing but the design rule checks. In this, the every metal has minimum width and minimum spacing. Those rules we will check in the DRC. The routing algorithms also will explain this on DRC also. Another is LEC, logical equivalency check. LEC is nothing but the equivalency between the pre and post design. What is this LEC? So actually you get the sensors and netlist. So there will be logical connection. If your design once place is completed, so many cells will be added, or so many cells logic restructuring is done. So even the changes are done, the netlist, the logical should not discard, right? So in the LEC, what you are checking is from initial netlist to the next stage netlist. So once sensors net to place once place is done, place to CTS, CTS to out CTS. We are checking the this all these netlist to the initial netlist in the sensors netlist. That is we are checking in the LEC. So once LEC is done, LV is done, DS is done. As a PNR engineer, we are doing all those things. And also there will be timing part also, STS static timing analysis. Actually in the PNR, what you are checking is you are taking the less corners. I mean less temperatures and less voltages. But in the real time, there will be so many temperatures, so many voltages. But all this, if you are executing PNR tool, it takes more time. So we are defining some corners. So if you have 12 corners, so you are taking only four of the corners, four critical corners, some critical corner, worst corner, best corner. So we are taking those corners, we are checking the PNR, we are performing the timing. Once you're done, we are giving this data to the STA team. The STA team perform the designing the multiple corners. Like they are multiple, they are checking in the 16 or 20 corners. So every corner should be there will be no issue, there will be no violation. Once everything is done, STA is done, there will be DRC free, it is LVS free, it is LES free, then it is perfect design. This is my role from floor plan to this STA. Once STA is done, the final stage is GDS, graphical data stream information interest chain. So once everything is done, so you have designed everything. So after that, we are giving the code in the GDS format to the designer. So there will be layout engineers, the layout engineers perform the layout. They are made in the connections like stick diagrams already we can study it. So by using stick diagrams, they design the layout. So once the design is done, everything is done, everything is bug free. So once everything is good, so we are giving this code to the GDS. So in the GDS, what the foundries. So this is nothing but GDS is nothing but foundry. In the foundry, before going to this also, we need to check the ESD, electrostatic discharge. What is this electrostatic discharge? Nothing but, so once package is ready, so your vendor design chip is ready. So chip is ready. Once chip is ready, if you are touching the external ports, there will be some static discharge from human to the ports. So we are considering that ESD also into the design. So by considering all those things, we will design we need to design by considering all these uncertainties. So this is the big task in chip designing. So once chip design done, we will give to the foundry. The foundry, what they will do is, as I said, they take the GDS code. This is the code they will take. Once that they take the code, they will design the design, and they will check the throughput. So the throughput is nothing but if them. So actually there will be shuttle. If one company did not go at a time the chip design, so it is a cost is so much of cost. So there will be multiple companies give their chips to the foundry at a time. So on the silicon wafer, one company chips are designed and some part, some other parts in other chip. So like that they are designing. So there will be shuttle. So if you miss the timing, so if I get the design right now, they give the time to 1 year. If you miss the 1 year time, that is so much of cost. So that's why, like some other companies, they in the drawback, actually they did not get the in correct time the chip. So let us consider Nokia is the very good company in older days, but in the when it comes to the smartphones, it is in back. So what is the problem? They did not give the that same technology in the correct time, then the correct schedule time. That is the drawback. And also in recently Intel also down the chips. You did not get the Intel processors as much of the the AMD processors and also the NVIDIA processors. The NVIDIA is the graphic processors, and also the AMD is the core process what you are designing. So if you design the chip, it should be in within time. So within time only the chip should reach to the designer. Then only it is the correct. If there is nothing, the company will drawback. They will lose so much of amount. See, this is the overall thing. So compared to the FPGA, the ASICs, we are taking so much of care while designing all those things, and also the technology shrinking from 300 nanometers to the 500 nanometers. There will be so many challenges. So if you go into the lower technologies, the channel is decreasing. So yeah, you have to consider all these things. These are all certainties we have need to consider, and by performing area, timing, and power, we are designing these chips. Okay. This is overall summary of FPGA and ASIC. Hello.
Right, sir.
Yeah.
Thank you, sir, for your wonderful lecture. Sir, there are a few questions to read out in the chat box.
Yeah, sure.
Sir, very few. There are a lot of questions are there. So why FPGA is faster than ASIC? That is one question asked.
Okay. Can I tell? Yeah.
Why FPGA is faster than ASIC?
Yeah. In FPGA, what we are using is we can design one chip. We are using that design to the multiple chips. Like we are depreciating the code. So if you write the code, we can use as multiple times, right? We can erase, we can execute. But in ASIC, we can't do, right? So one code is it is simple for simple designs only. We can do you can use FPGA, but longer designs you cannot do use ASIC. So that's why FPGA is faster. This is for simple designs like less gates. If you consider as I given in the slides, it is less than 25 million gates. So 25 million gates is very less. So that's why it is very fast.
Excellent answer, sir. Excellent.
Yeah.
What I expect you given to know. Very happy, sir. Thank you.
Yeah, any other questions? Actually, if it is the time constraints, we can mail to me also through Vasdev. So I will answer to your questions also. There will be no problem. In the real-time industry, what they will do and everything,
Sir,
I will explain. No
sir,
problem.
end of the query, sir, end of the query session, I think you share their WhatsApp number as well as mail ID, sir.
Okay, I will give the mail ID, but I did not give the WhatsApp number. Actually, I have so many work here. So through mail, you can contact me.
If you feel inconvenient, okay, you can share your mail ID. No problem.
Yeah, I will share the mail ID. If it is very critical or very urgent, you can take the
No, sir. No, sir.
number also from Vasudev.
Only we will compare the discussion. While we are using the design part, is there any problem we are facing? Just we have to interact with you. How to overcome from the issue. For that purpose
I didn't
only.
understand the question.
In the worst,
While designing,
sir, your WhatsApp number, when we will use, when we feel in the very difficult situation to proceed our design
actually,
process.
what is the problem is in the industry, we don't have so much of time. As a PD engineer, we have so much of work. So I may not give the correct time. So that's why if it is through mail,
Okay,
I will
sir.
give explanation.
No problem. Normally,
Yeah.
as any resource person will come, this question will ask. Okay. Then most of
Yeah,
them they
sure,
have
no
to
problem.
share their
Actually,
WhatsApp
I'm
number.
also former student from GMR IT, so there will be no issue.
Okay, no problem. Sorry.
Yeah. So it's okay. If it is okay, then there will be no problem. We can take from the Vasudev. It is okay. Any other questions?
Yes, sir. How can the effect of parasitics can be reduced in power planning?
In parasites in power planning, okay. So if you consider the resistance or capacitance, okay, the parasites is nothing but the resistance capacitance, right? If we have more resistance or more capacitance, that will be more delays. So as I said, in power planning, we don't use the less layers. We are using the higher layers. So I'll explain day after tomorrow what are the layers, what is this stack. There will be stack. If you consider the M1, M2, M3, there will be meta stack. So if you consider the lower levels, so those are having the less width. If you having the less width, there will be more resistance and more capacitance. To overcome this, we are using the higher layers. Higher layers is nothing but those are having the less resistance and less capacitance. Nothing but the more width and more spacing. So due to that, we can overcome the parasitics. And also in the chip, we are using the only RNC values. We did not use the L value. Capacitance we did not consider. Why? Because in the digital design, the rate of change, L is nothing but LE by dt, right? So the rate of change of current is very less. So within time, the data should be reached from one to other. So it is very less time. So that's why there will be no inductance affectance in the digital design. So when you go to the higher layers, I mean, in the total chip, you can use the inductance affectance also. Anything?
Sishanku ma'am.
Okay, sir.
Sir.
Sir,
Ma'am,
am I audible, madam?
ma'am, there are
Yes, sir.
many questions are there. I think we can send to the speaker so that it can be discussed in later session. Sai is having one more session, right, madam? Day after tomorrow.
Yes, sir. Yes, sir. Already guest has come and he has joined.
Yes, ma'am. Yes, ma'am.
Okay. Good evening to all. This is Dr. TVS Divakar from EC department. I am an associate professor. Sir, Mr. Manikanta sir, thank you very much. On behalf of EC department GMRIT, we thank you for your informative lecture. And on a brief, sir has covered logic technologies, ASIC versus FPGA design, and ASIC design flow, and how ASIC design cycle will work, and what are the advantages and disadvantages of FPGA, like slower performance, all these things. And also he has shown a simple design for understanding purpose for the audience. And also he has explained the different steps in the design of ASIC. So I think all the participants have gained more knowledge regarding these topics. And I thank Mr. Manikanta for his informative session. Thank you very much, all of you. The next session will start within 2 minutes or 3 minutes. Thank you all. Stay tuned.
Thank you, sir. Thank you so much. Thank you, team.
Thank you, sir.
Thank you, sir. Thank you so much, sir.
Thank you, Manikanta.
Thank you so much, sir, for your valuable insights. Definitely, we will work in the future, sir. Thank you.
Naveen sir?
మేడం సార్ జాయిన్ అయ్యారా?
Okay. Join అయ్యారు కదా సార్?
చూడలేదు మేడం.
చూసాను సార్ జాయిన్ అయ్యారు.
జాయిన్ అయిపోతారండి. ఓకే సార్. గుడ్ ఈవినింగ్ సార్. బాలాజీ సార్. సార్ గుడ్ ఈవినింగ్ సార్.
Joined and left us, sir. I have seen.
No, ma'am. Sari is there in meeting, ma'am. Professor N.
Okay.
Balaji name is there, ma'am. Sari
Yes,
is
sir.
also
Yes, sir.
unmuted.
Apologies, sir.
Sir, voice is not audible. Madam, సార్ వాయిస్ వినపడట్లేదు.
అవును సార్. Good evening, sir. Balaji, sir.
Unmute, sir. So, sir already unmuted, sir. Okay. Maybe there will be problem with the mic connection. Ma'am, otherwise once we can call to Balaji, sir.
Video off. Jagan Garu, am I audible?
Yes, sir. Yes, sir.
Right. You have muted
Perfectly
me.
audible, sir.
Right.
Yes, sir.
Okay.
Good evening,
So
sir.
let me share my screen.
Balaji, sir. Good evening, sir.
Good evening, madam.
Sir, we welcome you, sir. We heartily welcome you for this session, sir.
Thank you, madam. Thank you.
Thank you for readily accepting us.
Yeah.
Sir,
Sir,
let me call upon Dr. Geetama, sir, to introduce the guest.
Yeah. Is the screen visible for you?
Yes, sir. Yes, sir.
Fine.
Yes, sir.
Okay.
good evening, sir.
Good evening, madam.
Good evening to all participants. It's my pleasure to introduce today's resource person, Dr. N. Balaji. Dr. N. Balaji is a distinguished academician and researcher with a profound expertise in the VLSI domain. Currently serving as a professor in the Department of Electronics and Communication Engineering at JNT UK. He also holds the role of in charge Director of the University Legal Cell and Government Affairs at JNTU Kakinada. Dr. Balaji's academic journey includes a PhD and ME from Osmania University and BE from Andhra University, laying a strong foundation for his exceptional career. With 26 years of teaching experience in undergraduate and postgraduate programs, Dr. Balaji has held several key administrative positions. These include serving as a head of the department at University College of Engineering Kakinada, JNTUK, University College of Engineering Vijayanagar, JNTUK, and University College of Engineering Narsaraopeta, JNTUK. He also worked as a vice principal at University College of Engineering Narsaraopet, JNTUK, director of admissions at JNTUK, and director of internal quality assurance cell IQAC at JNTUK. He has been an executive member of Andhra Pradesh and Knowledge Mission, contributing to state-level educational initiatives. In the field of research, Dr. Balaji has successfully executed over 3 sponsored projects, including the principal investigators of collaborative ITRA, Information Technology and Research Academy, a division of Ministry of IT and Communications, sponsored project with a worth of rupees 3 crores. His innovative work is recognized through 3 granted patents published in the Patent Office Journal. Dr. Balaji has an impressive portfolio of academic contributions with 72 publications in international journals, 3 in national journals, 20 presentations at international conferences, and 8 at national conferences. He has also authored 2 books and monographs, furthering his impact on academia. His dedication to research excellence earned him the Best Research Award from JNTUK. As a director of IQAC, Dr. Balaji played a pivotal role in achieving NAC A+ grade for JNTUK and implementing green and energy audits. Thank you, sir. Thank you so much. Please continue the session.
Thank you, madam. Thank you for the introduction. So good evening to all the participants. So today I'm going to give the presentation on FPGA-based system for heart rate monitoring using approximate adders. So this is like a practical oriented related session. So most of the researchers will be doing the software kind of simulation. So as an electronics and communication engineer, it's preferable to show our outcome in terms of a hardware. So that's the reason why you all aware that ASIC and as well as the FPGA plays an important role in having a real-time implementations and as well as a visible outcome for whatever the research work that we do. So I have chosen a biomedical signal processing application. So here, if you see a heart rate variation that may contain various indicators and as that will decide various cardiac diseases. This is the scenario that you can see. The heart rate variability analysis, it became a popular non-invasive tool for assessing the cardiovascular conditions. So you can see how in the major cities, how the heart related anomalies are spanning over many years over the population. So there is a need for early identification of these heart anomalies. So keeping that in view, this particular topic was chosen. So you all aware that the ECG electrocardiogram, it presents the electrical activity of the heart, and it is widely used in the medical field, as we all know, because of its non-invasive nature. So it is widely used. And if you look at the ECG waveform, you can see that the P, Q, RS, and T. The QRS complex is most important characteristic of ECG, and each wave corresponds to an electrical phenomena included in the heart area, where the QRS complex reflects the ventricular depolarization. And this signal is mostly generated by detecting and amplifying very small potential charges on the skin. Say if any patient goes to the hospital, the electrodes will be placed on both sides of the heart, on either side of the heart, and then at various positions, and the ECG signal will be acquired. So this is the typical ECG signal. You can see that there is a PR interval, and then as well as a QT interval, which is longest interval that you can see. The QRS complex is so important, as you can see that there is a R peak where the amplitude change of this ECG signal this signifies that there is some kind of anomaly, and the tabular form that shows the P wave has an amplitude in the range of 0.1 millivolts to 0.2 millivolts, and their specific duration was clearly mentioned. Similarly, you observe that the QRS complex has a has the highest say you can say amplitude of 1 millivolts, and then the duration is of 80 milliseconds to 120 milliseconds. And this is a typical ECG signal, and we are going to particularly identify a particular heart rate anomaly called arrhythmia. So what is this arrhythmia? It is a kind of irregular heartbeat. So the irregular heartbeat, it may be too fast or as well as too slow or too early or irregular. So in various cardiac arrhythmia, again they are subdivided into myocardial infraction, and based on the types of heartbeats like left bundle branch block, based on the QRS duration, whether it is greater than 120 milliseconds, and if there is an absence of Q wave, then it will be a left bundle branch block beat, and then you can classify it as a myocardial infraction. Similarly, right bundle branch block. In myocardial infraction, there are two types of beats, like RBB and LBB, left bundle branch block and right bundle branch block. So all these are dependent on the duration of the signal, and as well as the presence of the wave or absence of the wave, or the time duration. So this is the kind of anomalies that can be identified. So this is what our implementation part. So you can see how an arrhythmia classification is done based on this block diagram. So the first step being, we will acquire an ECG signal. So after acquiring the ECG signal, normally the ECG signal is more prone to get affected with noise because of a smaller amplitude, and we will be placing the electrodes at various positions, and they will be in contact with the skin. Normally this leads to a kind of noise, and that noise is to be removed. So during the pre-processing stage of the ECG signal, this noise will be removed, unwanted noise will be removed, and you may use empirical modal decomposition, S-Gole filter, DWT filter, and Gole with discrete wavelet transform. So
excuse me, sir.
Yeah.
A screen sharing is missing, sir. We can't see the screen.
Yeah, right now?
No, sir. No? It's not visible.
Okay.
It is visible, madam.
Okay.
Visible, madam.
Yeah.
Okay.
So,
you can pin
visible, sir. Your screen is visible.
Fine. So the pre-processing of electrocardio ECG signal, cardiogram signal. So there are various techniques, but particularly in this research work, what we did is we have used a 5-stage filter, which we have taken from an IEEE journal paper, IEEE transaction. So I am acknowledging, and I'm showing that from which particular journal paper we have taken this particular implementation was shown there. And then we will be doing the feature extraction. Then finally the Arrhythmia beat classification. The outcomes being like normal sinus rhythm, which is indicated by N. If there is a right bundle branch block, R will be represented, left bundle branch block, like that. So we are going to give the beat classification. So this is what we are interested finally to analyze and show it as an outcome. So in most of the cases, the continuous monitoring of cardiac patient requires the personal care. And in this research work, FPGA-based hardware implementation of QRS complex detection was done. And a most popular, quite old algorithm called Pan-Tumpkin algorithm can be used. The new method is based on the center derivative and intermediate value theorem to locate the QRS peaks. And the authors has designed an architecture and implemented it on FPGA using a beautiful feature called Xilinx system generator. See, we are all aware of the Xilinx Vivado or Xilinx ISC. Now ISC is absolute, and now Xilinx Vivado is being widely used. So what this Xilinx system generator require is you need a MATLAB version or MATLAB software that should get installed, and a compatible system generator software. Just I'm minimizing these things, and just I'm sharing my desktop screen so that everyone can see this one, system generator. So I place the cursor on the icon called system generator. Is it visible? Screen desktop is visible for you?
Yes, sir. Yes, sir.
Yeah, this is a system generator, and you have a Vivado 2018.2 version where I placed the cursor. So you require a compatible MATLAB as well as the Xilinx Vivado version that need to be installed in the same drive. Like if I am see, my PC will be having C drive, D drive, like that. If I have partitioned my memory, hard disk memory into the drives, so in the same drive it is recommended to have an installation of these both Vivado, Xilinx Vivado version, and as well as the MATLAB version in the same drive. And there should be a system generator. Both should be the full version, like MATLAB full version, and as well as the system generator. This Vivado also the full version. So after the successful installation, you may be able to open this MATLAB, and if you click on there is a Simulink. This Simulink is nothing but the block diagram level entry. So just you can click on Simulink. So if you click on Simulink, it will open a new window, Simulink browser, without writing the MATLAB code. If I want to make use of the block diagram level entry, so this is the best way that we can do. Already, if I am using a Xilinx VLSI implementation, like FPGA implementation, there is a predefined Xilinx block set is there. So if I click on Xilinx block set, so it will give me various basic elements, communication related elements, various basic elements that you can see, like on the screen: slice, threshold, serial to parallel, reset generator. So you can see many of these basic blocks. So you can go back and then you can see what are the communication predefined block, like convolution encoder. So I need not write a Verilog HDL or a VHDL code for this one. So the convolution encoder is already a predefined block, so which I can just make use of this predefined block and use it for my implementation purpose. See, already there is a decoder called a Reed-Solomon decoder, and as well as encoder block is there, Viterbi decoder. So you can explore all these things, even for digital signal processing related, like fast Fourier transform. You need not write a big code for a fast Fourier transform. Just I can make use of this fast Fourier transform block. Just you need to have a blank model. Just click on the blank model. It opens a blank model. Just you need to drag and drop these in the blank model. So it is an untitled one, and you can here click on this one. So it gives you the Simulink browser, and then you can drag and drop the required blocks into your blank model, and you can make use of these predefined blocks. That's how you can easily do this. So this is a convenient way of implementing the designs with just with Simulink block set. Um, so this is one easy way of implementing the design. So that's a small introduction related to what is this Xilinx system generator. As we came across the term called Xilinx system generator. So just I have given a brief introduction related to the Xilinx system generator and how to access this Xilinx system generator for digital signal processor. And of course, the authors has used a Nexus 4 FPGA evolution kit. And what the authors has done is they have proposed an architecture, and they have validated it using a 48 hours of record obtained from MIT BAH database. So standard database which can be which is valid and authenticated throughout the world, that MIT BAH database of these ECG records that they have taken. And yeah, so the real-time monitoring of heart failure patients, especially people with cardiac arrhythmia, is a very important task. So for that particular task, the authors has proposed this particular architecture. So the hardware implementation using FPGA chips is most important in recent technologies. And these chips can be considered as, see, in the previous session itself, I think you have got the clear idea of FPGA versus ASIC. Both has certain advantages and disadvantages. FPGA has a greater advantage of reconfigurability and as well as the reprogrammability, which makes much more comfortable for some good number of applications. As you are aware, ASIC application-specific integrated circuit is particularly used where the functionality is fixed, and I don't want to change the functionality of that particular chip. Then I may prefer application-specific integrated circuit ASIC. And FPGAs are preferred to other programmable chips due to their specific purpose components, and of course low cost, reconfigurability I told, and their high parallel and interconnected architecture. This makes FPGA for some good number of applications. And in the previous 2 decades, various hardware implementation of QRS detection have been proposed. And as I told you, the most famous algorithm called Pan-Tamkin QRS detection algorithm, it is implemented on FPGA using earlier it was done with the Verilog hardware description language, so which is given in reference 1, improving the calculation performance. And then this calculates a threshold value for the next peak detection cycle from the median of the 8 previously detected peaks, and so on. So this is a kind of literature that does exist on QRS complex detection, was discussed in detail. So let us quickly go for the proposed system by the authors. The proposed detection system is mainly based on the algorithm, as we have repeatedly saying, Pan-Tamkin algorithm, but with the addition of new simple and efficient techniques in the detection stage. And they have implemented an FPGA chip using Xilinx system generator. So these are the 4 main contributions. So one is development of new technique for detecting QRS complex. Hardware implementation on FPGA chip is the second contribution by the authors. Validation of the implemented system on the whole of MIT BAH Arthemia records and real-time validation with FPGA evolution kit. So these are the four contributions by the author. So coming to what are the different materials and methods that the authors has used is the ECG, which represents the electrical activity of the heart, is widely used. Okay, of course, see we have done a detailed discussion regarding in the introductory session itself. So let us quickly go for the QRS detection algorithm related things. So after acquiring the ECG signal, the first step is the pre-processing stage, and in the pre-processing stage the noise will be removed. So generally for the removal of the noise we will be using different filters. Here the authors have specifically used 5 consecutive filters, beginning with a band pass filter, and then there is a derivative filter. Then the output of the derivative filter is passed through a squaring filter, and then there is an integrator filter, and finally ending with a low pass filter to obtain a smooth noise free signal. That's what the main aim of this pre-processing stage. Internal to the pre-processing stage, there are 5 consecutive filters which are given as band pass, derivative filter, squaring filter, integrator filter, low pass and low pass filter. So 5 different stages. Then the next stage is R peak detection stage, where if the amplitude of the signal is above the threshold or below the threshold, if it is above the threshold, you'll be able to tell some anomaly does exist, and which is itself composed of 3 parts: R peak detection, taking the centered derivative, detecting the maximum peak of the R peak, and then thresholding on amplitude and time. And it is shown in figure 2. So we are going to talk about QRS complex detection and use of different filters. So as we discussed, 5 consecutive filters that they will be used. So this is the entire block diagram of heart rate monitoring system. So you observe after acquiring the ECG signal, it is passed through the first filter called band pass filter, then derivative filter, then squaring, then integrator filter, and then finally the low pass filter. That low pass filtered output is given to a QRS detection stage, which consists of center derivative, maximum peak detector, then adaptive thresholding is used for the decision making, like whether the patient has the anomaly or not. Then even the heartbeat or heart rate calculation is done, and finally the arrhythmia detection stage and display of arrhythmia detection class is the final outcome of this particular implementation. So these things, now the question comes, why should I go for FPGA or the ASIC implementation? Why not just a simulation? So you observe the software implementation versus the hardware implementation. If you make a comparison, the software implementation is sequential in nature, like instruction by instruction will be executing in the software, so which makes which takes more number of clock cycle, and which consumes more time, whereas in the hardware implementation is concurrent in nature. So you may execute 2, 3 or 4 number of instructions parallelly. So the hardware implementation is concurrent, and the software implementation is error prone, and whereas the hardware implementation is robust. The software implementation require the programming skills, whereas the hardware implementation require the design skills. For example, if I want to implement a filter, say FAR filter or IR filter, so y of n is equal to h of 0, where h of 0 is the filter coefficient multiplied with x of n, an input signal plus h of 1 into x of n minus 1. So by looking at the equation, it is of the form sum of the products form, so which requires a number of multipliers and as well as the adders. So in the hardware I need to design an adder and as well as a multiplier, and then in making use of these adders, multipliers, I need to design a filter. So this requires the design of design skills, hardware implementation, whereas the software implementation requires the programming skills. So that's the difference. And software implementation is of low cost, and whereas the hardware implementation requires the significant cost because you need to buy separately the hardware, the components, and other things. So there are well-developed programming methods in software, whereas in the hardware implementation, hardware prototypes, they are very hard to build. So this is again whatever we have discussed in the tabular form, the hardware versus software implementation. So you can see the on-chip hardware implementation is necessary for all real-time applications. So we will come across the term called real-time application. So let us look at what is meant by a real-time application. So the real-time systems are real-time application. What are the real-time systems is nothing but execution of application with strict timing constraints is called a real-time system. Again, you can divide the real-time systems into hard real-time systems and as well as the soft real-time system. So what is meant by hard real-time system is if there are catastrophic effects, if I don't follow the timing constraints, then it is called hard real-time system. For example, if you have a control system of an aircraft, in the control system of an aircraft, no delay is accepted, because that leads to the catastrophic effect of having the threat, life threat for many people who are traveling in the aircraft. So the lives of people depend on the correct working of the control system of the aircraft. Then it is a hard real-time system. Whereas a soft real-time system, though there is a delay or it can be accepted. So in soft real-time system, accept lower performance for the delay, and it is not catastrophic when deadlines are not met, and it will take longer to handle one client with the vending machine. So for example, if I in most of the airports you may see a vending machine. By selecting a particular item, you may get from the machine. So where even some delay is there, it is acceptable. It is not catastrophic, and it's not harming anyone. Probably you may be get a little delay while delivering the item from the vending machine. So that is an example for a soft real-time system. See, because we are saying this is used for real-time application, so we should be aware of what is a real-time system and real-time implementation. Nowadays, hardware and software implementation, they are commonly used in different fields of application. Although the amount of software implementation is widely prevalent, there is an integrated implementation methods which combines the hybrid software and hardware approaches. The hybrid approach will benefit from the software learning capabilities in the aim to attain efficient real-time hardware. That is like a FPGA circuit implementation. For instance, most systems are developed and implemented in software when particular task does not require as much speed. So the hardware implementation is particularly necessary for time-consuming application. The most important limitation is to respect the real-time constraint, and we discussed about what is a real-time system, hard real-time and soft real-time. So coming to the block diagram of heart rate monitoring system, we need to implement these all these blocks in the heart rate monitoring system. That is the important task. See, why do you require these filters? They find wide variety of applications, not only noise reduction. If it is an image processing application, you want to modify or enhance the image or videos or data. So you can use that in image processing for smoothening, sharpening, and noise reduction. And particularly in this application, we are using these filters for particularly removing the noise from the biomedical signal which we have acquired, and then we are giving it to the next stage as an input. So you can broadly categorize your filters into analog and digital filters. So FIR and IR filters are the two popular digital filters that we widely use. And these digital filters, they are very crucial components in signal processing system with the demands for low power and high speed and area efficient implementation. This particular research work explores the integration of, see, the authors has done the implementation of these filters with adders and multipliers. So what we have done is we have replaced the adders with approximate adders. So we have taken a very recent research paper on approximate adders, and then we have compared the accuracy of the conventional adder with that of the approximate adder, and we found it is giving a satisfactory accuracy, and without losing the accuracy, we want to have a balance between the accuracy and as well as the performance. So this is what the modification that we did, like replacing the adders and multipliers that are being used in the earlier research work. This is a simple and small modification that one can look at. Even replacing adders and you have a multiplier, so replace your say multipliers with adders and shifters, so that you can reduce the number of multipliers. If there is a reduction in the number of multipliers, there can be reduction in the complexity, reduction in the number of hardware resources that are being utilized by your implementation. So these are quite old and existing ideas only, so not quite new. So a small effort was made of replacing the conventional adder with that of the approximate adder. Furthermore, the designed filter with approximate adders, they are used in ECG signal processing and continuous heart rate monitoring, which provides optimal area, optimal power consumption and high performance without compromising the accuracy. So I'm not going to discuss about FIR and IR filters. It's a known fact. So what are the filter requirements? Any type of filter design involves large number of adders and as well as multiplier. See, we discussed that, for example, if you take a FIR filter equation, y of n is equal to h of 0 into x of n plus h of 1 into x of n minus 1 plus h of 2 into x of n minus 2. So it is of a typical sum of the product forms, which demands number of adders and as well as the multipliers. So for better performance in a particular application, so low latency adder you may use. So in this particular work, what we did is low latency dual sub adder was taken, which provides lower delay and lower on-chip power consumption when compared to the normal adder. So this is a small block diagram of a basic digital filter that one can look at. So the quotient need to be multiplied with an input signal x of n minus of minus 1. So it is said to be as x of n plus 1, and there is a time delay block, there is a multiplier block, and finally there is an adder block, and the y of n output of this filter is taken at this extreme right hand side, and extreme left hand side, of course, you are applying an input x of n. This is the block diagram of a low latency dual sub adder, and the block diagram, you have a precise adder block, and then you have your input operands like A, B, and your carry out signal you can see here. and as well as the sum and carry are the two important outputs of any adder. So this is the block diagram of a low latency dual subadder, and this is the comparison and error logic of this adder. If the predicted carry and actual carry are the same, then obtained sum is correct and no further error correction is required. If they are not correct, the error logic block is used, and resultant carry C not the CP and C out. If C is equal to 0, carry is equal to 0, obtained sum is correct and error correction is not required. If the carry C is equal to 1, then error correction is required. Okay, and yeah, so if is LSB bit of upper subadder output is 0, then it is changed to 1, otherwise it is not changed. So this is just about an example of how whether the error is an acceptable one, how to correct the error. A simple logic, an example was shown here. And if you want to implement this low latency dual subadder in Xilinx system generator, as I have shown you, so you need to open your Xilinx system generator. Okay, just click on Xilinx system generator. It opens this particular Xilinx system generator block, and you can have your the Xilinx system generator block and dual latency subadder. So here you have a pre-processing stage in which you have a band pass filter in which you can see an adder or subtractor block. Okay, and then you have a delay element and you have the constant multiplier. C multiplier is a constant multiplier. Is the screen visible? Is the model visible? Whatever I am showing?
Yes, sir.
Yes, sir.
Yeah. So, so you can observe in the pre-processing stage, you have 5 different filters that are available, and you may implement these. Okay, making use of the Xilinx system generator. So you have a constant block. Okay, constant, two constants I want to give. There are gateway in and gateway out. So these things just you can search and you can browse. So here if you say gateway in, okay, so you can browse these elements. So here you got the Xilinx system gateway in. This is the block which you can drag and drop onto your the new model of your Xilinx system block. Even if you place that, it will be showing gateway out block. It converts the Xilinx fixed point or floating point type inputs into outputs of type Simulink integer single. So you may even get the description about those blocks. So you can simply make use of these Xilinx system generator blocks, and you can easily make. And this is nothing but the block box, and inside the block box your logic will be there. Okay, like adder related logic or implementation will be there, and then gateway out, and finally the display. Just to simple implementation of the adder using Xilinx system generator block is shown. And after the implementation of this low latency dual subadder, it is compared with the conventional adder, and you can observe that for this one, the total power computation was done, and then the approximate dual low latency dual subadder had just a total power consumption of 7.0192 when compared with the conventional adder, giving a 32.4% reduction. So you may use this kind of adder in the heart rate monitoring system implementation. The QRS detection algorithm has two main stages. So as we discussed, band pass, derivative filter, and squaring, integrating, and low pass filters. So you can implement this one, making use of a Xilinx system generator. So let me go for this implementation part. So you have a input, and here in the pre-processing stage, so here is the entire block diagram. This ECG data will be taken from the MIT BIH database. So we can take the ECG data. So the ECG data is taken in ECG.mat file is there. Just let me show you the ECG.mat. So in which 100 people data was taken from this one. Okay. So just you need to click on the load ECG.mat. So this particular file contains the ECG data, so which you need to load before running this particular system generator implementation. Okay, fine. So this is how we are accessing the ECG data. This ECG data is applied to a gateway input, okay, and then it is given to a pre-processing stage. So if you double click this pre-processing stage, what is inside that pre-processing stage you can look at. See, it consists of band pass filter. So how do I implement a band pass filter is making use of the adder, subtractor, and constant multipliers. So you need this particular details of how I implement a band pass filter. Similarly, it is given to a derivative filter. So how the derivative filter is to be implemented is again you making use of the Xilinx system generator. So this is the block diagram of a Xilinx system generator block. I think this visibility is fine.
Yes, sir.
Difficulty in visibility.
Yes, sir. Yes, sir. Yes, sir.
It's fine.
So you can observe clearly there is a delay element, there is a constant multiplier. So the input is given here to the constant multiplier, and after the delay it is passed through again another constant multiplier, and then given to an adder, and then finally see here you have a divider block. Okay, if so this is what a derivative filter in pre-processing stage. The other one is a multiplier, and then there is an integrator filter. So inside the integrator filter you observe that how the integrator filter is implemented is making use of the various delay elements. So this particular, you can observe that almost there are 53 delay elements were there, and okay, this is an integrator filter. And in the pre-processing stage you have a low pass filter. Low pass filter is a quite easy and a smaller one. There is an adder or subtractor, there is a delay element, and you are making use of only 3 constant multipliers. Output of these 2 constant multipliers, multiplier 2 and multiplier 3 is given to an adder or subtractor, and then you can obtain the output for this one. So this is about the pre-processing stage. If you go to the R-peak detection stage, which is the next one where QRS complex detection is done. So this is a quite big task, and peak detection and heart rate calculation for this one. This is the main one which you need to implement. Okay, in making use of Xilinx system generator. So you have various adders and subtractor blocks. Okay, in QRS peak detection you have the registers, delay elements, there is a counter. Okay, and So the counter is like a drag and drop. Even similarly, register constant blocks. Okay, there is a divide generator block. Okay, and this is given. See, even there is a provision of converting a .m file into a Xilinx system block. Okay, that you can explore, just making use of the help menu that is available in your system generator, that you can easily explore. So this is the implementation of a QRS peak detection, and class decision. For this one, you need to make use of the two constant and relational, like when A is greater than B and A is less than B, and giving it to a final like a multiplexer kind of these things, that you can use a simple class decision block that you can use, and based on your decision, if your output is a logic 0, then there is no heart rate anomaly is not there. If it is 1, some heart related anomaly is there that can be displayed, and another output is given to a what do you say, to the display of heart rate, number of heartbeats, like 66 beats. And there is a beautiful feature called scope, just like the oscilloscope that we use, where we can view the waveforms. So because this was already done, just if I run this particular model, it will be able to give me the output related to this one. So this is a detailed band pass filter implementation of the band pass filter, derivative filter, integrator filter, and squaring filter. So detailed description related to each and every filter was given. Band pass filter, ECG signal is first band pass filtered in the range of 5 to 15 hertz using fourth order recursive filter, which reduces the false detection caused by various types of interference present in ECG signal. So why the band pass filter? Why the first stage is band pass filter? Here is the justification for this particular usage of the band pass filter as the first filter. What is that justification is? The ECG signal is band pass filtered in the range of 5 to 15 hertz is the band pass range, using fourth order recursive filter, which reduces the false detection which is caused by various types of interference present in the ECG signal. The next filter is a derivative filter. Now this is the second filter which we are using. Purpose of this filter is to extract the slope information of the QRS complex. A derivative function, this particular derivative function is required, and the derivative filter implemented using Xilinx system generator block. XSG is Xilinx system generator block set and approximate adder. Information about the slope of the QRS is obtained in the derivative stage. So the purpose of this derivative stage is the slope of this particular QRS can be obtained in the derivative stage, and this is what the implementation of a derivative filter. It consists of 3 delay elements here in the first stage. In the second stage, you have 4 constant multipliers, as you can see here, and the output of these 4 constant multipliers are given to these block boxes, and then there is a constant, and then there is a divide block, and these 2 outputs are given to this divider block, and then finally the output of this derivative filter. Output of this derivative filter is given to a squaring filter. What the purpose of a squaring filter is, a nonlinear transformation is performed by calculating the square of the derivative signal, and this allows only positive values and increases the contrast between large and small amplitude. By squaring, you can get the contrast between the small and larger amplitude, and only you will get a positive value, because we all know like -1 whole square is +1, -2 whole square will get +4. So only positive values will get by squaring, and it increases the contrast between large and small amplitude so that the noise can be removed very easily. That is what the purpose of a squaring filter. And then comes the integrator filter. This is nothing but the moving window integrator produces a signal which includes the information about both the slope and width of the QRS complex. Even the time duration of the QRS complex need to be known. That is the reason why we'll use an integrator filter which gives both the slope and as well as the width, which gives us the time duration of this QRS complex. A moving window integrator filter is applied to the squared signal, which consists of n number of delay element. So in our case, I think we have done like 54 delay elements were taken based on, which is typically equal to double the QRS width of 150 milliseconds for sampling frequency of 360 hertz. So we are going to calculate how many number of delay elements based on this calculation. N is equal to 0.15 into 360 hertz. So we got 54 delay elements based on these 54. We have used 54 delay elements in the integrator filter. This you can clearly observe in your Xilinx system generator model just by clicking the pre-processing stage, and then you click on the your integrator filter, where you can clearly see that there are 54 delay elements starting from delay 0. This is delay 0, delay 1, and so on up to delay 53. So there are 54 delay elements. So why 54? You got now the justification, because we are having a QRS width of 150 milliseconds and a sampling frequency of 360 hertz. Based on that, we calculated how many number of delay elements. It comes around 54 delay elements. And the next last filter is a low pass filter. The transfer function, the output of the integrator, is smoothed by first order low pass filter. The transfer function of that first order low pass filter is 0.00865 plus 0.00865 z power -1. So that means this is a delay element divided by the denominator term. In order to obtain this kind of transfer function, we have used an adder cum subtractor and a constant multiplier. There is a delay element here, then one more constant multiplier, and then the output of these two constant multipliers is given to an adder, and then final output of the pre-processing stage. So let us try to see whether we are able to get an appropriate output for this one or not. Let me go to the system generator block set, and then you just click on this run button. So it compiles. Okay, it takes a few seconds for the successful compilation, and then now the compilation is over. Okay, now the running of this, just double click on the scope, so it opens a new window. Okay, the scope window. So in the scope window, you can observe that you have divided into the various sections. The first one being the ECG data that you have given at the input side, and then you have the second one is the peaks that got detected. See, these peaks are important whether the patient has some kind of heart anomaly or not. Can be known by the detection of these peaks. And then what kind of arrhythmia that the patient is suffering can also be obtained by this third one, arrhythmia detection. And the last one is the heart rate, and how the heart rate is varying with respect to the time. On the x-axis you have time in seconds, and on the y-axis here you can see the amplitude in both your peak detection and as well as arrhythmia detection. Of course, ECG data is taken for 100 patients, which is taken from MIT BIH database. And in the case of heartbeat, here 0 to 100 on the y-axis was taken, and on the x-axis you have the time in seconds, which was clearly displayed. Now, coming back to this one, so we have we can implement using the conventional adder. The authors has implemented using the conventional adder, whereas in our case we replace the conventional adder with an approximate adder, and we find we are not going to lose much accuracy with the approximate adder. And in fact we have got with the integrator better outputs than the conventional adder, and then even the low pass filter output, we got a very smooth low pass filtered output. And peak detection and heart rate calculation, for which we will be using the center derivative and as well as the maximum peak detection, and the peak detection can be done. So for the implementation of the peak detection and heart rate calculation, this is the block diagram. Not block diagram, Xilinx system generator diagram. This is a Xilinx system generator diagram where there will be a centered derivative, and there is a maximum peak detection block, mean R to R interval of the last 5 detected QRS peaks, amplitude validation block is there, mean amplitude of the last 5 detected QRS peaks is there, and final block is a heart rate calculation block. So this is peak detection and the heart rate calculation block, which we have implemented making use of the Xilinx system generator. Just if you double click this particular block, inside that Xilinx system generator block, this entire Xilinx system generator implementation was there, so which you can see clearly that this can be implemented using Xilinx system generator block. And when the heart rate is less than 50 or above 120, then it indicates that the patient is diagnosed with arrhythmia disease, and your output is like, if I get a 1, then arrhythmia disease is there. If I get a 0, then there is no heart disease. And you can do the software simulation, and you can see that when I think I have shown you the this one, heart rate monitoring related one. You can see here 0 and 66. Once again, if I run this, yeah, so yeah, you observe that in the display 0 means that there is no arrhythmia and the number of heartbeats are 66. So that means if the heartbeats is when there is a anomaly is, we already discussed that if the number of beats is less than 50 or above 120, so it's not like the case. So we got 0 and 66 or 68 sometimes. Okay, because we have taken both heart rate anomaly and the ordinary patients data also in the 100 patients database, which we have applied to as an input for this one. And these are the output signals which I have shown you in the scope, and the synthesis and implementation results of these can be shown here using the conventional and approximate adders. And not only just this simulation, what you can do is you can target an FPGA board. So how that can be done is explained here. The Xilinx system generator based hardware design, you want to have a display block. Displayed the output of arithmetic detection block on 7-segment display of Arctic 7 FPGA board we have taken using VHDL block. The 7-segment and anode output obtained from the display block is assigned to the corresponding 7-segment LED and anode pins on FPGA block. So there is a gateway out 3 in the Xilinx system and the Xilinx gateway. So in the Xilinx system generator block, okay, this is your gateway out. Okay, this gateway out, this is the gateway out. Okay, you see, you have, when you click on this one, you will get various options like Xilinx block add, Xilinx by tools, all these will be there, format, okay, HDL code, PLC code, all these you will be able to get. Okay, so here, so the gateway out, so you can configure this gateway out 3. The Xilinx system generator based design simulated in MATLAB and Simulink can be implemented on actual FPGA using hardware co-simulation. The process for implementing hardware co-simulation in system generator is click on system generator icon, okay, and choose VHDL language. So you have a system generator icon. So you can click on this system generator icon, and can you see here system generator icon? When I click on this one, it is asking me for the board. Okay, you have a wide variety of board selection here. Can you see here?
Yes, sir. Yes, sir.
You have various FPGA boards. You can like Kintex Ultra Scale, Z board is there, Arctic 7, Kintex 7, like that, Vertex 7, Zinc board. See, all these boards are there. So you can choose those appropriate board which you are having. Okay, and click on system generator icon and choose VHDL language. So again, I'm going back to this Xilinx system generator block, and if I click on this, here you have a hardware description language. See, you want to have the hardware description language as VHDL, choose VHDL, or you may have an option to choose Verilog also. Okay, and VHDL. I have chosen VHDL and default library. Compilation is hardware co-simulation. And you can have an IP catalog, HDL netlist. You have settings. The target directory, see, you may browse and you can give your appropriate path for target directory. And of course, these are like default flow, performance optimized high. Okay, and Vivado implementation defaults, and you can choose the performance explore like post-root related, and then you have net delay high performance, like that you can choose. So you're not bothered. So just you may choose with this Xilinx system generator this option. Choose the particular FPGA board. If the required FPGA board was not shown, then we have to add the required FPGA board files to Vivado software, and by writing a startup.m file, it will add those boards to Xilinx system generator. We have added Arctic 7 FPGA board files for implementation. So we will give add path, get environment, Xilinx Vivado, so scripts and system generator, Xilinx environment setup board file repository as In D drive, I have Vivado 2018.2 version, and then we have added this Edge A7 board. See, this Edge A7 board is not available as a board. Okay, so we have a big, because this board is not available in the list of these FPGA boards. We have added this Edge board, okay, Edge A7 board, as that FPGA should be supported for FPGA implementation. Okay, and then the hardware software co-simulation. So I have shown you these options. This is what I have shown you, like choose the FPGA, appropriate FPGA board, and it is of course a part of Arctic 7 board. Compilation is like hardware software, hardware co-simulation, and other options were chosen. It will generate a bit file block, connect the required inputs and output blocks to the generated bit file block like JTAG in a new .slx file. Connect the FPGA board to your laptop or a desktop computer with the JTAG cable and click on run button. Then the design will be processed on FPGA board and the output can be seen on the personal computer. So this is what you can see. This you can see on a laptop, and to the laptop through the JTAG cable, the FPGA is connected and the FPGA is programmed through the JTAG cable. And once the programming is done on the LED display, you can see the heart rate, how much is the heart rate, and the glowing LED indicates a logic 1 and a non-glowing LED indicates a logic 0. So this is how you can even implement on the FPGA, and you can see there is another beautiful feature called ChipScope Pro that you may use, and then you can display the waveforms like this on the display. See, we used a scope, and then that ChipScope Pro feature, particularly from the FPGA pins, you can extract the output and display, making use of the ChipScope Pro feature of your Xilinx system generator. So this is a simple implementation, FPGA implementation of a heart rate monitoring system. This one can make you without having much HDL knowledge or difficulty in HDL implementation. You may use the available Xilinx system generator blocks, and you can have your own maybe the Xilinx blocks, and then you can implement very good number of applications, and then you can show those as the hardware implementation. So with this, okay, with this few remarks, I'll close this session.
Thank you, sir. Thank you for your presentation.
Thank you, sir.
Shall we go for a question, sir, from the that
Yeah,
are reflected in the participants?
Yeah.
Sir, the first question is, sir, by this software, can we generate code once we complete the design?
So what is the question? Why the software?
By this software, can we generate code once we complete the design? By this software, can we generate code once we complete the design?
Yeah, see, I told you, like, you can entire this one without system generator, you can happily implement. If I am very much confident on VHDL or Verilog coding, so for every block I can write a VHDL or a Verilog code, and then I can comfortably implement it on the hardware like FPGA, I can program. So I think the earlier speaker might have given you the number of steps. So we will write a VHDL code, then simulate, then synthesize, then of course translation, mapping, placement, and routing. All those will be taken care by the Vivado IDE. And finally, a dot bit file or a dot hex file will get generated, and with that we can just program the FPGA. That's it. So there is no compulsion that we should use the system generator tool. There is no this thing. Just this is if I am not that much comfortable with my HDL coding, and then I am getting a number of errors in my HDL code, like either VHDL or Verilog, then I may opt, I may go for this kind of Xilinx system generator, a block diagram level entry, and then I may go ahead. That's it. So there is no compulsion, like I must use this tools, Xilinx system generator tool, need not be. Like if I am a HDL expert, so I may prefer the HDL code itself. No need of this tool, like Xilinx system generator need not be used, need not go for this tool at all.
Thank you, sir. Thank you for your response. Sir, one more question, sir.
Yeah.
How to set up and hold times are calculated for both adder circuits?
Yeah, how to?
How setup and hold times are calculated for the adder circuits?
Yeah, so see, the tool itself has given these time calculation. So we have not done a particular specifically like the manual computation. Just it has given that, and that was displayed. That's it. So there is no specific calculation part. So the tool itself is giving its the provision is there. Just in the Xilinx Vivado, so you have tools like X power tool for power calculation and other aspects. In a similar manner, you can have that setup time and hold times calculations, and the tool itself is given that. So there is no separate manual computation or something else need not be done.
Thank you, sir. Thank you, sir. Is there any questions from the participants? What name for this FPGA?
So what?
What name for this FPGA?
The FPGA is nothing but it is an Arctic 7 FPGA. So the company has put its name as Edge A7. They had added some other peripherals, and then they have given a name. So it is basically Arctic 7 FPGA.
Okay.
Excuse me, sir.
Yeah.
Sir, myself Venkatalakshmi, sir. So thank you, sir, for giving explanation. And one more doubt is, so Xilinx generation is there, sir. You explained very well. So in that Xilinx generator, so 54 delay elements, sir, came. You already explained, sir. 54 delay elements are sampling theorem 360 Hz. So in that delay elements, whenever increases, there when reach the output, then it's very time delays. So much amount of time occurred when reach the output. So this is there any reduce the delay elements, sir? Is there any possibilities?
Yeah, see, you can try for the reduction in the number of delay elements by maybe by adopting say like we have the frequency, sampling frequency, and the QRS width, right? The sampling frequency is taken as 360 Hz, and then we came across the number of delay elements as 54 delay elements.
Is there any possible, sir? Is there any possible to decrease the delay elements?
Yes, that's what. So the number of delay elements depends on your QRS width and the sampling frequency. So if I am compromising here, so there may be other. So it's better like focus on I told you, if you have a multiplier delay, see, try to reduce the multiplier delay instead of reducing the number of delay elements. So I may focus on somewhere like in place of a multiplier, replace the multiplier with an adder and shifter. The delay of adder and these shifter elements is much less when compared with a multiplier. That's where I can try to reduce the delay instead of reducing the number of delay elements.
Okay, sir. Okay. Thank you, sir. Thank you.
Instead of focusing on reducing the number of delay elements, I may focus on reducing the delay because of the other multiplier blocks and other blocks. Wherever
So one more.
Yes.
Sir, one more, sir. Is there a sampling frequency fixed 360 Hz, sir, or is fixed,
No,
sir? Is it?
It's not like that. So here in this particular case, we have done for this for a sampling frequency of 360 Hz. So it depends on for a sampling frequency of 360 Hz and this one. See, you can get a better this thing when you see this particular paper. So I have given the acknowledgement and listed this paper. So 2019, the title of the paper is FPGA based system for heart rate monitoring. It's a 2019 IET Circuit Devices and Systems, volume 13. You may go through this particular research paper. You will get a better
okay, sir.
yes,
Okay,
better explanation. We have taken this as reference paper. Of course, we did some changes like replacing the adder with a approximate adder and other changes we did, and then we have
elements also, sir. Okay, yeah,
yes,
sir. Okay.
yes. Please go through this specific paper, so you will get a better you will get better understanding and better explanation from this particular research paper. Even I think in the first slide itself, I think I have given this paper. I think 1 minute. So at the every slide acknowledgement was given with the author name and as well as the title of the paper and the journal name and year, volume and page numbers. I clearly mentioned. So you may please go through this reference paper. You'll get a better explanation for every aspect.
Okay, sir. Sir, can you send this PPT in that
I will
group?
share this PPT with Mr. Naveen. So Dr. Naveen, and then you may get access for this presentation.
Okay, sir. Thank you, sir. Thank you so much, sir.
Yeah.
Thank you, sir, for our response. Is there any questions from the participants? I think no questions are there, sir.
Yeah. Thank you, Dr. Naveen, and thank you for the GMRIT management and ATAL FDP for giving me this opportunity that just to share my little knowledge about these implementations. Thank you once again for all the participants, despite of this late hours, your patience and your active participation and the questions that you have asked really encourages us to give the better presentations. Thank you very much.
Thank you, sir. Thank you.
Thank you, sir. Thank you, sir.
Thank you, sir. Good evening to each and everyone.
Thank you, sir.
Good evening to each and everyone. This is Dr. N. Prasad, Senior Assistant Professor in EC Department, GMRIT. It's my privilege to deliver the vote of thanks for this 6-day ATAL FDP program on VLSI design innovations for defense applications. First and foremost, I would like to extend my heartfelt gratitude to our chief guest, Dr. N. Balaji Garu, for gracing this event with their delivering an inspiring and interesting topic on FPGA-based system for health monitoring. Your words have been truly enlightening and have set the perfect tone for today's gathering, sir. On behalf of EC Department, GMRIT, we are saying heartful thanks to you. Thanks to you, sir, for attending this session and sharing your knowledge on FPGA-based system for health monitoring. And sir, you have explained very interesting topics on electrocardiogram, ECG signal processing, how to remove the noise, what are the pre-processing steps required for that ECG signal processing, and what tools are required like MATLAB and Xilinx tools integration for this FPGA architecture implementation and various research papers discussion. And heart rate monitoring system block diagram, a very, very interesting facts, sir. And all these information really helpful for us. And on behalf of EC department, I'm GMRIT, we are saying heartful thanks you, sir, for sharing your knowledge.
Thank you, Dr. Prasad. Thank you. Thank you.
And I would like to thank our organizing committee for their hard work and dedication in ensuring this event was a success. Thank you for all the participants for engaging your time to attend this ATAL meeting. Thank you to each and everyone who are present in this meeting. Have a good night, sir. Thank you, sir. Thank you.
Thank you, sir. Thank you so much, sir.
Thank you, sir.
So, dear participants, the day 2 feedback link is given in the chat box. So please fill it and submit it before 9:45 p.m.